Hi guys, it's time for chapter 1. We're going to study interactions in motion. This is chapter 1 of the course of matter and interactions, and I'm actually in a bit of a bind here because I don't have a lot of time, so I'm going to have to rush through this a little more than I would normally like to. But it turns out the old video somehow has sync issues after all these years, and I don't know exactly how, but what are you going to do? So, we start with chapter 1. First thing I want to point out is that this course is based on 3 fundamental principles. The first is the momentum principle, which we're going to begin in earnest in chapter 2. It says that the change in the momentum of a particle over a period of time is equal to the net force acting on the particle. That's the degree to which the surroundings exert a net force on the particle, or on the system, times the time over which that net force acts. And of course this principle is most accurate if the time interval is very small compared to the time over which the net force can change. So if the net force is not constant, we have to use a time interval that's small compared to the time it takes for the net force to change very much. So this is an approximate principle with that restriction. The energy principle, on the other hand, is much more exact. It says that the energy of a system changes when the surroundings do work on the system, or when heat is transferred in or out of the system. So we're going to use that principle to study changes in energy. And finally, the angular momentum principle is the one that talks about how the thing rotates and how it spins. Angular momentum has to do with the rotation of a system, and much like the momentum principle, the angular momentum principle relates the change in the angular momentum to the net torque acting on the system over a period of time. And again, if the net torque is not constant, the time interval has to be small compared to the time over which the torque changes very much. But what's interesting isn't the details of these 3 principles, but it's that you can encapsulate so much physics into 3 fundamental principles like that. These 3 principles are going to last us pretty much the whole semester, and we're going to be doing many different systems with many different behaviors, but they all boil down, all these various systems and behaviors and interactions and so on boil down to these 3 basic principles. So if there's anything you learn in this course, it's going to be what these 3 principles mean and how they work and what you can do with them. So that's going to be the focus. Also, we're going to be using a tool this semester called VPython that is a 3D animation and visualization tool. It's open source, and you can go and get it right now if you want to. It's at vpython.org. I encourage you to download it, install it on your own personal computer, and you can use that to explore a variety of modeling tasks. We're going to be doing most of our modeling in class in a kind of a laboratory setting. But there may be times when I encourage you to try something out at home, and for that reason it'd be nice if you had the tool there. So go ahead and download it and become familiar with it. In order to talk about matter and interactions, we have to discuss what kind of matter are we dealing with. At the sort of basic level, you know that the universe is made up of atoms, and so that's sort of a fundamental kind of matter we're going to deal with. Of course, you probably also know that atoms themselves are composed of electrons, protons, and neutrons. And you may know that protons and neutrons are actually not elementary, but have subcomponents called quarks, and so on. But for the most part, most of the time, we'll be dealing with larger objects, that is, combinations of atoms. Atoms can combine to form molecules and solids, liquids, and gases. And we'll be dealing with those at various points in the course. And of course, these materials can combine to form planets and star systems and galaxies and all of the visible universe. So all of the matter we handle can be thought of as atoms clumped together, combined together in various ways to form different kinds of stuff. And pieces of matter interact with one another in a variety of ways, and we're going to study several of them. But what happens when there is an interaction? Can you look at a piece of matter and see, just by observing it, whether or not it's undergoing an interaction at this time? And the answer is you can. If you see the object just sitting there, not moving, not changing anything, then it's probably not interacting, at least not interacting very strongly. It has no net interaction. It's in stable equilibrium, say. But if you see it changing its speed, that means there must be an interaction of some kind with something. How could you detect a change of speed? Well, you could take a series of snapshots at equal time intervals, and you could witness the position of the object at the time of these different snapshots. And if you see the distance between one snapshot and the next snapshot changing with time, that means there's a change in speed. And so that means that the thing is undergoing an interaction. On the other hand, you could keep the distance constant, but change the direction along which the object is moving. That would also be indicative of an interaction of some kind. So if the speed is constant, but the direction of motion is changing, that also requires an interaction. And of course, these two properties, direction and speed, are nothing other than the elementary properties of the velocity vector. The velocity vector is a vector whose size is the speed and whose direction tells you which way the thing is going. And if the velocity vector is not constant, that means there's an interaction. In fact, this is formalized through a thing called Newton's first law. Newton's first law basically says if the velocity vector is constant, then there's no interaction. If the velocity vector isn't constant, then there is an interaction. An object undergoing no interaction will have a constant velocity vector. That means it will move at a constant speed in an unchanging direction. Now, there are other things interactions can do. They can cause changes in identity. You can change one kind of particle into another kind of particle, or they can change an object's shape. They can change its temperature. We're going to postpone consideration of those kinds of changes until later in the semester. For now, we're going to focus on changes in motion. And so that's going to be what we'll be doing for a few weeks. In order to describe motion, position, velocity, momentum, force, and acceleration, we're going to need the concept of a vector. A vector is a mathematical object that describes how big a thing is and in which way it points. So, for example, how much velocity have you got? That's called the speed, the amount of velocity, and the direction of the velocity is which way the vector points. And I've got some resources you can look up to help understand that, which I will point out here momentarily. We do need to be able to do stuff with vectors, like add and subtract them. We need to be able to multiply them by a number, a scalar, which is not a vector, like 3 times a vector is a vector that points in the same direction, but it's 3 times the size. We need to be able to get the magnitude and direction of a vector given its components, and we need to be able to find unit vectors and direction cosines of vectors given their components. So we'll do that in the homework. We'll also do a little bit of that in class so you get an idea of how it works. And the notation we're going to be using is either the I hat, j hat, k hat notation, with which you might be somewhat familiar, or the angle bracket notation, where you put the 3 components inside angle brackets separated by commas. Some of the quantities that we'll be using vectors for are position, the r vector, velocity, the v vector, p, the momentum vector, and capital F, the force vector. So these are, and there are others. We're not done with that. There's acceleration, and I don't know, probably a dozen different quantities that are vector in character. But these are the main guys. And I have cooked up a vector video that you guys can go and look at. I put a URL up on ACE that you can click on if you don't feel like typing. But that is the URL. And I hope you have fun with that if you decide to go take a look at it. Just a note on vector notation: if I have a vector that has x component of 4 and a y component of 2, you could write that as 4i hat plus 2j hat, or you could just write it as 4, 2. And if I have another vector with a x component of 1 and a y component of 3, you could write it as I hat plus 3j hat, or using the angle bracket notation as angle bracket 1 comma 3. And if I add those two together, notice you add the x components together and you add the y components together to get the resultant vector. Then they just add up to 5, 5. So that's an example. Let's look at velocity as an example. There's this idea of average velocity. If I have a displacement, delta x, over some period of time, delta t, the average velocity is the ratio of delta x to delta t. Let's take an example. Let's say I have an object originally at x1, then it winds up at x2. The displacement is the difference between x1 and x2. And supposing that that takes some period of time, I divide by delta t and I get the average velocity as a vector that's equal in direction to the displacement vector, but has a different size because you divide by the time it took. And so, for example, let's say x1 is 5, 1, 0, and x2 is 8, 5, 0. What would delta x be? Well, delta x you'd get by subtracting x1 from x2, and you'd get 3, 4, 0. If the period of time was 3 seconds, you'd end up with an average velocity of 1, 1 1/3, and 0 as the x, y, and z components. And of course the units are going to be meters per second. So I really, if I had been paying attention, I would have put meter units on the position x1 and the position x2 and the displacement delta x. They should really have units of meters. But I grabbed these slides from years ago, and apparently I wasn't as careful back then as I should have been. But it should be meters per second. Okay, what about a position update? Well, you can run this average velocity equation backwards. In other words, if you know the average velocity and you know the time, you can compute the new position given the old position. So let's say we know the old position is 510 meters. I should have meters there. And I know the average velocity is 1 and 1 1/3 meters per second. And I know the duration of the time interval was 3 seconds. The idea is I can compute the displacement by multiplying the average velocity by the time interval, 3 seconds, to get the displacement. Then I can add the displacement to the initial position to get the final position. That's the idea. Alright, so you can use the initial and final position in the time to get the average velocity from the displacement, or you can get the new position if you know the average velocity and the time and the old position. So we're going to use that in the modeling, because to figure out where a particle is at a later time, all we need to know is the average velocity over the time interval and the old position before, at the beginning of the time interval. Now momentum is defined as that monstrosity. It's the mass times the velocity vector divided by this terrible square root. Now the thing is, that terrible square root has a velocity divided by the speed of light in it, and if the velocity is much, much less than the speed of light, then 1 minus v over c squared is really very, very nearly equal to just 1. So for motions that happen at a very low speed, much lower than the speed of light, you can neglect the v over c squared and just treat that as mass times velocity. So for many problems where we're not dealing with relativistic speeds, where speeds are close to the speed of light, sometimes called relativistic speeds, then we can forget about the square root business and just use mass times velocity. But if there's a problem where something's going at half the speed of light or 2/3 of the speed of light, you're going to have to take that speed of light part into account to calculate the momentum. Let's do an example. In this case, let's say we have a particle moving with a speed of 3, 4 meters per second. In other words, has x component of 3 meters per second, a y component of 4 meters per second, and a mass of 3 kilograms. How do we calculate the momentum? Well, we take the square root of the sum of the squares of the components of the velocity. That's notice that's just the Pythagorean theorem, and we work out the velocity, or the speed, the magnitude of the velocity is 5 meters per second. Of course, 5 meters per second is much, much less than 3 times 10 to the 8 meters per second, which is the speed of light. So we can forget about the square root in the relativistic correction to the momentum, and we can calculate the momentum as simply mass times velocity. So the momentum is 3 kilograms times the velocity, 3, 4 meters per second, and so the momentum is 9, 12 kilogram meters per second. To calculate the rate of change of momentum, I'd have to calculate the momentum at the beginning, the momentum at the end. subtract the two momenta and divide by the time. That would give me the rate of change of momentum. We're going to find out that that is nothing other than the net force. That'll be chapter 2. But just so you see that we're not just calculating momentum for the fun of it. We need to know the momentum in order to determine what happens as a consequence of the interaction. So that's all I have for you for chapter 1. I'll see you guys next time. This is chapter 2, the momentum principle. The first thing we need to sort out is the concept of the system and the surroundings. When you're working on a problem, it's important to divide the universe into two parts. There's the part you're interested in, or the part you want to focus on, and that's called the system. The rest of the universe, the uninteresting part, is called the surroundings. What you choose as interesting and non-interesting is completely up to you. It's determined entirely by your notion of convenience. What's the simplest thing to do under any circumstances? So there's no correct or incorrect way to divide the universe. The main point of this chapter is the focus on momentum change. The momentum of a system changes when it interacts with its surroundings. Such an interaction can be described using the concept of force. Force is a vector that points in the direction of the interaction and whose magnitude is equal to the size of the interaction. All this boils down to a fundamental statement, which is the main point of this chapter, called the momentum principle. The momentum principle says that the change in the momentum of the system is equal to the net force, or the net amount of interaction between the system and its surroundings, times the time over which that force acts. The force is the interaction. It's exerted on the system by the surroundings. Let's look at an example. Let's say we have a mass of 2 kilograms moving with an initial velocity of 3 meters per second. That gives us an initial momentum of 6 kilograms meters per second in the x direction. You can think of that as a vector that points in the positive x direction with a length of 6 kilogram meters per second, or a magnitude of 6 kilogram meters per second. The force acting on this mass is negative 10 newtons. It's pointing in the negative y direction with a magnitude of 10 newtons for a time of 1/10 of a second. The momentum principle says that if we multiply the net force of interaction on the system by the surroundings by the time over which the force acts, 1/10 of a second, we'll get the change in the momentum of the system. That's a consequence of that force. We can simply multiply. It's a scalar multiplication by a vector, so we end up with a change in momentum of minus 1 kilogram meters per second in the y direction. In other words, a change in momentum of magnitude 1 kilogram meters per second, pointing in the negative y direction. You can think of that as a vector that has a magnitude of 1 kilogram meters per second and points in the negative y direction. The final momentum is the sum of the initial momentum, our 6 kilogram meters per second in the positive x direction, and our change in momentum, the negative 1 kilogram meters per second in the y direction. We can simply add those vectors together, remembering that vectors add by components. So the x components add, the y components add, and the z components add, giving us a net momentum, or final momentum, of 6 in the x direction, minus 1 in the y direction, and 0 in the z direction, all in units of kilograms meters per second. You can think of this as a vector sum, where you've got the initial momentum, the change in the momentum, and the final momentum, the vector sum of those two vectors. Now we know how to update the momentum of a system which is undergoing an interaction with its surroundings. The next question is, how do we update the position? Remember, when you update position, you need to use the average velocity over the time interval. When a force acts, the velocity is not constant. It varies. How are we going to estimate the change in position when the velocity is changing? We have to use the average velocity over the time interval. In order to calculate the average velocity, it turns out small time intervals work better than large time intervals. And over a small enough time interval, one reasonable approach is to use the arithmetic mean of the initial and final velocities. It turns out the arithmetic mean is exactly correct in the limit when the force is constant. If the force is not constant, then the arithmetic mean is less and less correct. Let's look at an example with a constant force at a speed much less than the speed of light. Since the force is constant, it turns out the momentum principle is exact for any size time interval. Remember that the momentum principle is it's approximately correct if the time interval is small, and the smaller the time interval, the more exactly correct it is. In order to decide how big of a time interval you get, you have to think about how much is the force changing during the time interval. It's nearly correct as long as the force doesn't change very much. So for example, we know that the final momentum is the initial momentum plus the change in momentum, but if the velocity is much less than the speed of light, then the velocity is simply the momentum divided by the mass. So I can divide both sides of this equation by the mass, and I get that the final velocity is the initial velocity plus the force, which is constant, remember, divided by the mass, times the change in time. If I put that into the average velocity, the arithmetic mean of the initial and the final velocity, which is correct as long as the force is constant, then I end up with the expression that the velocity is equal to the initial velocity plus 1/2 of the force divided by the mass times the change in time. If you've had physics before, you might recognize that the force divided by the mass is simply the acceleration. That's the rate at which the velocity vector is changing. Of course, once we have the average velocity, we can use the position update formula from last week. That is, the change in the position is the average velocity times the change in the time. Putting that all in, we get the final position is the initial position plus the initial velocity times the change in time plus 1/2 the force over the mass times the change in time squared. Continuing with the idea of an example, let's get some specific numbers in there. Let's imagine we have a 3/10 kilogram ball thrown from the origin with an initial velocity of 2,010 meters per second. In other words, 2 meters per second in the x direction, 0 meters per second in the y direction, and 10 meters per second in the z direction. But it's under the influence of a constant force of 3 newtons acting in the negative z direction. What's the velocity and position of the ball at some later point in time? Well, we have two update formulas we need to apply. One is the velocity update formula. Remember, this works when the force is constant. We put in the force, we put in the initial velocity, and we get an equation that tells us that the velocity at some later time is 2 meters per second in the x direction, 0 meters per second in the y direction, and 10 minus 10 times the change in time meters per second in the z direction. Similarly, we can use the position update formula, putting in the initial position, the initial velocity, and the force to calculate the final position at any point in time. We get that the final x component of the position is 2 times delta t, the y component is 0, and the z component is 10 times the change in time minus 5 times the change in time squared. So for example, after 1 and 2 seconds, respectively, the final position is 205 and 400. Notice that after 2 seconds, the object has reached 5 meters in the z direction, but at 2 seconds, it's back down to 0 again. Whereas in the x direction, the motion is uniform. It starts at the origin at 0 seconds. At 1 second, it's at 2 meters. At 2 seconds, it's at 4 meters. And you can guess at 3 seconds, it would be at 6, and then 8, and then 10, and so on. It's useful to visualize what's happening here to use a graph. So I've made a couple of graphs of what's going on here. We've got the graph of the x and z components of velocity, and graphs of the x and z component of position, called just x and z. First of all, I want to look at the velocities. The x component of velocity is constant.
This makes sense because a constant x component of velocity implies a constant x component of momentum. Remember, the force only acted in the z direction, so that means the change in the momentum occurs only in the z direction. The x component of momentum is constant. On the other hand, in the z direction, the z component of momentum has to be changing, and it's got to be decreasing, because the z component of momentum is changing by the force that acts in the z direction. On the other hand, the velocity is the rate of change of the corresponding position. So the x component of velocity is the rate of change of x. The z component of velocity is the rate of change of z. So you can see that the x position is increasing at a constant rate because the x component of velocity is constant. On the other hand, the z component of position increases at the beginning. In the middle, it's not increasing at all, and at the end, it's actually becoming more negative with time. And that's also consistent with the z component of velocity. Now, there are some more complicated kinds of problems we can have where the force is not constant. So, for example, we can have different knowns and unknowns. Maybe we do know the force and we do know the change in momentum, but we don't know the time, and so on. We could have more than one force. Remember, it's the net force, or the sum of all the forces, that causes the change in momentum. As I said, we can have non-constant forces, and finally we can have multiple particles and multiple objects. At that point, we can decide to make the system all the objects together, or sometimes it might be useful to pick one of the objects and make that the system and treat the other objects as the surroundings. So there's different approaches you have to take, and it just takes practice to learn how to do that. We'll go over some examples on Wednesday of homework problems and so on, but just be aware that once you've got the basic idea, there's different ways to apply those ideas. Finally, I want to point out the notion of the conservation of momentum. First of all, the momentum of the universe as a whole is always strictly conserved. That means if you take the momentum of the system plus the momentum of the surroundings, added together, the total momentum of the entire universe always is the same at the beginning and the end of any problem. This makes sense because the momentum principle can apply to the system or to the surroundings. But the force on the system due to the surroundings turns out to always be the opposite of the force on the surroundings due to the system. And so if you work it out, you can see that the change in the momentum of the surroundings is always the opposite of the change in the momentum of the system. So when you add them together, the total change in momentum of the entire universe is always 0. If you have a problem where the system doesn't interact significantly with its surroundings, then it means the change in the momentum of the system is equal to 0. In other words, the final momentum is equal to the initial momentum. In that situation, we say that the momentum of the system is conserved. But of course, we know that in all cases, the momentum of the system plus the surroundings is conserved. Anyway, that's really all there is this week. We'll do some examples on Wednesday and see how this stuff works.
Hi guys, welcome back to Chapter 3. It's time for fundamental interactions and some other interactions as well. Let's see what it's about. First of all, we're going to be dealing with forces that are definitely not constant in this chapter, and that means, for example, the gravitational force, which arises when you have two objects separated by some distance in space. So a typical example would be a planet and a star, or maybe two stars, or perhaps a planet and a spacecraft of some kind, or maybe a planet and an asteroid. Of course, this force acts between all masses, even a tomato and a bowl, or a bird and a tree. But the force, if you consider such small objects with so little mass, this capital G here, the universal gravitational constant, is such a tiny number that the force produced by two relatively tiny objects is so small that it is hardly worth taking into account most of the time. In order to produce an appreciable magnitude of force, you need huge masses like planets and moons and things like that. So most of the time when we're dealing with this force in any practical way, at least one of the masses involved will be rather large. Now that's in contrast with the electrostatic force, which is the force exerted on one object by another, where both of the objects have some amount of electrical charge, a net charge of some kind. And the charge is measured in a unit called a coulomb, and unlike the gravitational force, where the masses are always positive numbers, when we're dealing with electrostatic force, the electric charges can be either positive or negative. So we'll spend some time talking about these relationships, but all I want to point out at the moment is the remarkable similarity between the expression for the electrostatic force and the expression for the gravitational force. The r hats represent a vector that goes from the charge or the mass producing the force toward the object that experiences the force. So the r hats tell you which way the force points, essentially. Notice that the gravitational force has a minus sign, and if you think about it, the fact that there's a minus sign there and the masses are always positive means that the gravitational force is always an attractive quantity. The force always points in a direction toward the other mass that's producing the gravitational force. The electrostatic force, on the other hand, if the two charges are equal in sign, either both positive or both negative, it ends up with a positive sign, which means the r hat vector and the force vector point in the same direction, which means that the force on the other object is repulsive. They tend to repel. On the other hand, if the two charges have opposite sign, that automatically introduces a negative sign in front, which means that the force points in the opposite direction from r hat, and that means the force is attractive. So the electrostatic force is somewhat richer than the gravitational force in that it can be attractive or repulsive depending on the relative sign of the two charges. The other point that's worth noting is that unlike the gravitational force, if I calculate the acceleration on mass 2, I would divide the force by mass 2, and I'd get something that depends only on mass 1. So we get an acceleration due to mass 1 that's independent of the amount of mass in mass 2. But with the electrostatic force, if I divide the electrostatic force by mass 1, or mass 2, excuse me, notice that now the acceleration depends on the relative charge to mass ratio of particle 2. So it no longer is independent of the properties of particle 2, but it depends on the detailed proportion of charge to mass in particle 2. So you don't get fixed amounts of acceleration from an electrostatic force as you do with the gravitational force. A couple of other forces that we are going to be dealing with are the force of a compressed or stretched spring, which was introduced in Chapter 2, but we're going to be working with it in more detail in terms of predictions of motion this week. And then there's also the force of air resistance, which we sort of touched on last time when we did the coffee filter modeling lab, but we'll talk about this in more detail this week and get some sense of how that works. It is a velocity-dependent force as opposed to a configuration or position-dependent force. All right, so how do we handle problems where the force is not constant? Because all four of these examples generally arise in such a way that the forces do not remain constant. And the answer is we start with a particle moving with some momentum. We compute the force acting on the particle. Then from the force and the amount of time that's going to elapse, we calculate the change in the momentum using the momentum principle. Given the change in momentum and the original momentum, we can easily add the two together to get the new momentum. Once we have the new momentum, we can compute the velocity of the particle, the new velocity. If we have the old velocity and the new velocity, we can get the average velocity and then extrapolate the motion of the particle to get the new position of the particle. Now, oftentimes, it's going to turn out, especially when the time step is small, that it's not worth the trouble of computing the average velocity, but it's almost is accurate to just use the new momentum to get the new velocity and use that in the position update formula to get the new position. So that's what I'm going to show here on the slide. Once we get the new position, we can use the new momentum and the new force. Notice the new force at the new location is different because the force may depend on location, it may depend on velocity, but it's certainly not going to be constant. So we get the new force, we get a new change in momentum, we add the change in momentum to the old momentum to get the new momentum, and again we compute the new velocity, extrapolate the position of the particle to the new location, and we basically repeat this process over and over again until we're happy. We can adjust the time step in order to ensure accurate predictions, and we can let the computer do most of the work in order to compute what happens to the particle. So that's the basic idea. Let's do an example to see how this works. I want to study the example of the motion of a block resting on a spring, where the spring starts out compressed, and so the block is going to end up wiggling up and down. Let's talk about the forces that are going to act. We'll have the weight on the block due to the Earth, so it's the force on the block by the Earth. And we already know from the last chapter that that's proportional to the mass of the block, and the proportionality has to do with the strength of the gravitational field, this gravitational field vector G. Then we've got the force on the block by the spring, which is proportional to the displacement of the block from the displacement of the end of the spring, I should say, from its equilibrium or unstretched position. And that goes like minus the spring constant times the distance of the spring, the end of the spring, from its unstretched place. And we add those two together and we get the net force. And we're going to just calculate the net force over and over again as the block moves up and down to calculate where it goes. And central to this are the update principles for momentum and position. And if you were, hopefully you were there the other day when we did the modeling experiment with the coffee filters. But the basic code looks something like this. The net force we compute by calculating the displacement of the end of the spring from its equilibrium position or its unstretched position, and multiply by the spring constant, and then we add to that the weight. The weight is just the mass of the block times the gravitational field strength. And then we update the momentum, recalculate the velocity, that's the momentum divided by the mass because the speed is slow, and then update the position. And I just want to point out that you can replace you don't actually have to compute the final velocity, you can simply compute the updated position as the momentum times the change in time divided by the mass. So that's exactly the same thing, I just skipped having to independently compute the velocity since we don't actually need it generally. Alright, let's look at some code and see how this works. Okay guys, let's look at this code for the spring. I will post this code on ACE so you can take a look at it and you can download it and play with it if you want to. Basically, we set up the relaxed length of the spring and the initial length of the spring, so it's initially compressed about 10 centimeters. And then we're going to make the mass something like 1/8 of the unstretched length of the spring, so that you can see it on the screen. And then we have a time step of 100th of a second. We're going to have a spring constant of 8 newtons per meter, and initially we'll have a mass of 60 grams, or 0.06 kilograms. G, of course, is the gravitational field. Start the time at 0. So here we make a display that's a square 600 by 600 display with a tidal mass on spring with force arrow. The spring itself is a helix. You don't have to worry too much about that. The block is a box. The force arrow is a green, going to make it a green arrow, and initially it's going to be let's see, it looks like it's going to be at the center of the box but over to the right of the box by twice the size of the box. We'll start the momentum out as a 0 vector, and we'll start r as a vector at the initial position of the block. then the equilibrium position of the end of the spring is going to be the spring position plus the length of the spring. Notice that the spring, let's see, it starts at minus the length of the spring over 2, and it has a initial length L minus half the size of the block, but its unstretched length is L0. Then we compute the stretch. What's the stretch? Well, it's the position of the block minus the equilibrium position of the spring with no block. And the net force, of course, is minus the spring constant times the stretch plus the weight of the block. Then we're going to calculate the axis of the arrow by simply taking the force divided by 4. And that just scales the force arrow so that it looks nice on the screen. It's obviously the arrow is going to appear in real space on the screen, and we need to scale the size of the force arrow so that it fits on the screen nicely. And let's see, we'll have the, hang on one second here, got to move stuff around just a little bit. Okay, so and also the force arrow is going to be located in the y direction at the same height as the block, so it'll move along with the block. We're going to wait for a click from the mouse, and then we're going to run the thing 100 frames a second, and look, the physics is all right here. So the physics is update the momentum using the momentum principle, then update the position using the position update formula. Remember from the slides that the velocity is the momentum divided by the mass, so this is nothing other than r plus velocity times dt. That's the physics right there. And here we're going to update the position of the block on the screen with the new r, and then update the spring so that it looks right on the screen by resetting its axis. And then what are we going to do down here? We have to recompute the stretch and recompute the net force so it's ready for the next time step. So the stretch is the position minus the equilibrium position of the spring. The net force is exactly the same expression that it was before, minus the spring constant times the stretch plus the weight. And here we're updating the arrow, the force arrow, its position and its length to reflect the new force and the new position of the block. So let's run this thing. You get an idea what it looks like. And I'm going to move the window here just a little bit so it looks right in the movie, and we're going to go. Notice it goes quite fast. We're going to find out later how to predict how fast the thing goes, but that's a little too fast to see. So what I'm going to do, just to show you how you do this kind of thing, I'm going to dial down the time step just a little bit. Let's make it 0.2, 5 times smaller, and we'll run it again. And then you'll see that you can kind of see what's going on here is as the block goes above and below its equilibrium position, the net force gets bigger and smaller, and of course changes the momentum of the block according to the momentum principle, and the thing wiggles up and down about like you'd expect. So that's the way it works. What are the main points of all this? The main point is that you break the time up into little chunks of time step here, 2/1000ths of a second. Every 2/1000ths of a second we reevaluate the force, we reevaluate the velocity, and update the momentum and the position according to the update formulas that we learned in Chapter 2. So that's the idea of that one. Great. Okay, now let's talk about that gravitational force in a little more detail. We have an expression for the gravitational force, but how does that actually work? Let's say we have a particle m1 located at r1 and a particle m2 located at r2. So we have a position vector r1 and a position vector r2. We want to compute the force on mass 2. So the first thing we do is to calculate the position of mass 2 relative to mass 1, and that's simply r2 minus r1, right? Get a unit vector that points in that direction. That vector is called r hat. Then the force we compute by simply plugging in the numbers for the two masses. The magnitude of the r21 vector, that's the position of mass 2 relative to mass 1. That magnitude goes in the denominator squared, and then we multiply the whole thing by r hat, and then the universal constant negative g. Okay. The next force we need to discuss is the electrostatic force. It's very similar. We have a charge at r1, we have a charge at r2. We calculate the relative position of charge 2 relative to charge 1, compute the length of that vector and get a unit vector, and then plug numbers in to calculate the force. That's the idea. In this example, I've assumed that Q1 and Q2 have opposite charge, but of course, if they have the same charge, then the r hat and the force vector will point in the same direction. And that's all there is to it. Pretty straightforward. Let's look at a demo of a gravitational force acting on two stars as they orbit one another. Okay guys, I wanted to go over a little code here having to do with the gravitational force between two objects. So again, we have a display. It's 800 by 800. I'm going to define an AU as the distance between the Earth and the Sun, and then we'll use AUs in our program as a distance unit. The mass of the Sun, of course, is a solar mass. The gravitational constant you're familiar with, and I'm going to use for the T, the capital T, is a year. That's the time it takes our Sun to go around once. It's approximately pi times 10 to the 7 in seconds. Then we're going to make a couple of spheres to represent the two stars. One will be red and one will be yellow. Now, these spheres are going to be huge compared to the actual size of our Sun, so we can see them in the scene. I'll start one out at +1 AU in the y direction and the other at -1 AU in the y direction. And then what we'll do is we'll make one star have the mass of our Sun, and the other star will be half the mass of our Sun, so that the orbit is more interesting. If we made them both the same mass, then they would both be circular orbits, which would nothing wrong with that, but this is more fun. And we'll start the time out at 0. I'm going to start the initial velocity out at 2 pi times 1 AU divided by t. That's the distance the Sun goes in 1 year divided by the time it takes to go around, so that's a reasonable initial velocity. And we'll make the time step 1,000th of a year. The F0 is going to be a constant, which is basically g times m1 times m2 over 1 AU squared. And I only wanted to calculate that in order to develop a scale that would be reasonable to use to represent forces. So then we'll go on, we'll set the initial momentum of the first star up, and then the momentum of the second star I'm going to set equal to the negative of the momentum of the first star. And the reason for that, of course, is so the total momentum of the two stars is 0. That means that the center of mass of the star system is going to be stationary. So, and we can talk about that more in class. Then we'll go ahead and create a couple of curve objects to follow these guys. And what's the main point? The main point is that the physics is all done down in the loop here. R is the R vector from star 2 to star 1. So star 1's position minus star 2's position. R hat you can get by getting the norm of R. Norm is just a function in Visual Python that calculates unit vectors. And the force is exactly what we used in class. It's the gravitational constant times the product of the masses divided by the magnitude of R squared. You get a minus sign out here that makes the force attractive. And of course R hat is the unit vector that points in the r direction. Here's the momentum principle. The star 1's momentum is incremented. Plus equals is a way to increment by so much. It's incremented by an amount f times dt. Star 2's momentum is decremented by the same amount because of the reciprocity principle. The force on star 1 is plus f. The force on star 2 by reciprocity is minus f. So we don't have to separately calculate the force on star 2. We know it's just going to be the same thing except with an r hat vector that points in the opposite direction. So we can just use minus equals.
and then we increment the star 1 and star 2's position vector with the corresponding momentum times dt divided by the corresponding mass. So this is the same position. So we got momentum update, we got position update. Then we update the force vectors in the 3D image, and then and the force position of the force vectors and the axis or length of the force vectors. Then we're going to add to the curve objects which show us the orbit, and then start the whole thing over again. So the basic layout of the loop is calculate relative position, calculate force, momentum principle, position update, and then update the force vectors. And that's all there is to it. So let's run this code so you guys can see what it looks like. There go the two stars. Notice because their masses aren't equal, the orbits are not circular, but you can see that the two stars are rapidly moving when they get close together, and they slow down when they're far apart, and the force vectors always point at each other. So the two force vectors are always attractive, and that's the way it works. All right. All right. The last thing I want to say before I sign off for today is that there is this idea called reciprocity. And you notice that the equations for the force of gravity between the force of gravitational attraction between two objects is symmetric. In other words, the force on object 1 due to object 2 is equal and opposite to the force on object 2 due to object 1. And that's also true for the electrostatic force. And it's generally true that if one object exerts a force on another object, that there's an equal and opposite force of the first object acting on the former. And that's called Newton's third law. And your textbook calls it the principle of reciprocity. I like the title or the name reciprocity because it gives you some sense of what it means, whereas Newton's third law doesn't tell you anything about what it means. It's just a label. But the reciprocity means that there's a reciprocal relationship between any two forces, that when one object exerts a force on another, there's a reciprocal or equal and opposite force acting back on the first object. And we're going to hit this over and over again. I'll do some demos in class of big trucks colliding with little cars and things like that. And hopefully you guys will come to believe that it, not only do you understand the principle, but you'll actually believe that it's true. All right, we'll see you guys next time. So welcome back. It's time for Chapter 4. We're going to talk about contact forces and how they arise and how they relate to the momentum principle. So the first thing I want to point out is that we have a model of solid materials that we're going to be developing. And you could kind of think of it as a bunch of atoms connected together by bonds, which we're going to represent as little springs. So basically the chemical bonds will be thought of as little springs, and they're going to form a cubic lattice. Now in real materials the lattice can be somewhat more complicated. It can be a lot more complicated, but the essential features of our model of matter are all in the cubic model. The complexities that you get by going to other crystalline structures are interesting, but they're not fundamental. So we're not going to deal with those here. If you want to take a course in solid state physics, you can get all the detail you'd like about that. I wanted to give you a sense of what it looks like as you're sort of moving through this model. The idea is that it goes on and on and on for a long way, and that it repeats systematically and reproducibly. There's a constant distance from one atom to the neighboring atom, and there's a spring constant that exists between neighboring atoms, and it's always the same. So let's talk about those atomic bonds. The idea is they behave like a spring. So if the atoms are at their natural distance apart, if there are no forces acting on the material, then there will be a certain distance between neighboring atoms, and if you try to stretch them, they'll produce a force that tries to pull them back. If you try to compress them, they'll produce a force that pushes back. So they're always trying to get back to their unstretched condition. The actual physics of what's going on, of course, is that there's a nucleus and an electron, sometimes many electrons, that interact with one another in order to form this sort of behavior, to develop this behavior.
And for as long as you don't squeeze the thing too much, it's a pretty good approximation to treat it as a simple spring. If you look at real material, you can see that it ends up looking something like this. This is an actual atomic force microscope image of atoms from a crystalline solid, and you can see that it looks just about like our model. So it's not so bad. Let's talk about density. Density is the amount of mass per unit volume in a material. If the atomic separation is about the same for different kinds of materials, and the atomic mass is basically proportional to the atomic number, so by making some simple assumptions, we can develop a connection between the microscopic properties of the atoms, the distance between the atoms and the amount of matter contained in the atoms, to macroscopic properties that you can measure easily in the laboratory, like density. And the idea, of course, is that the density is the mass per unit volume. So you can see, looking at the picture, that the mass enclosed in that little cube is the mass of a single atom. And the volume of the little cube, the volume that's sort of associated with that atom, is simply the cubic distance between neighboring atoms. So let's see how that works out. Let's look at copper. Copper has an atomic weight of about 64 grams. That means 1 mole of copper has a mass of 64 grams. They call it molar weight, but really what they mean is mass. Excuse me. And another way to think about it is that the nucleus of copper has 64 nucleons, and that means that the mass of 1 copper atom is 64 times the mass of a nucleon, of approximately 1.7 or so times 10 to the negative 27 kilograms. The density of copper is going to be the mass of 1 atom divided by the volume of 1 atom, because the whole notion is that the atoms distribute themselves in a way that each of them gets the same volume, and the overall density is just the density associated with one particular atom. So you can compute the mass of an atom by dividing the mass of a mole of copper by Avogadro's number, or you can multiply the mass of a nucleon by the atomic weight, the atomic number. Molar weight, I guess, is the best way to say it. Okay, in this case it's 64. So if you calculate that out, you get a density of 89,400 kilograms per cubic meter. Actually, you could just go look this number up, or you could measure it in the laboratory, and then you can work it backwards to get the volume occupied by a single atom, and then you could take the cube root of that volume to compute the size of the cube, the side size of the cube, which is the distance between neighboring copper atoms. So you can see that by starting with the density and knowing the relationship between the atomic mass and the volume of the cube in which the atomic mass lives, we can go back and get the distance between atoms. Let's talk about the bond stiffness. In class, we measured the stiffness of a macroscopic spring hanging at the front of the room, and you guys all told me how you thought it would go when I hung 2 springs together end to end, and then we did the same thing with 2 springs side by side and so on, and we discovered that the spring constant of 2 springs hung end to end was less than the spring constant of the 2 springs individually, and in the case of 2 equal springs, it was the spring constant of 1 spring divided by the number of springs in the chain. And when we hung them side by side, you discovered that the spring constant was double. If you take 2 equal springs and hang them side by side, the effective spring constant of the combination is double. And then we went on to generalize that a little bit to talk about, well, what happens if we had a long chain of springs all connected together and then neighboring chains connected together side by side. And what we decided was that the long chains would have a spring constant equal to the spring constant of one of the springs divided by the number of springs in the chain, and the side-by-side chains would have an effective spring constant of the number of chains times the spring constant of a single chain. So let's write that all down. If you take springs end to end and you think of the spring constant between neighboring atoms as the intrinsic bond strength, and your textbook calls that Ks, I. The intrinsic bond strength divided by the number of bonds would be the spring constant of one chain. And then the spring constant of the material, if you think of a macroscopic wire as a bunch of chains hung side by side, to get the spring constant of the entire wire, that would be the spring constant of a single chain times the number of chains that are dangling there side by side. That's the idea. Now the number of bonds is the length of the wire divided by the bond length, and the number of chains is the area, the cross-sectional area of the wire, divided by the area occupied by one chain, which is just d squared. So if you take those expressions for the number of bonds and the number of chains and plug them back into our expression for the spring constant, you get the interesting result that the spring constant of a macroscopic wire is the bond strength times the number of chains divided by the number of bonds in a single chain. And if you put in what we worked out based on the length of the wire, the area of the wire, and the bond length, the distance between neighboring atoms, then you get the final result that the spring constant is the bond strength between neighboring atoms divided by the distance between neighboring atoms times the ratio of the area of the wire to the length of the wire. That's how it works out. Now, if you plug in numbers for copper, as your textbook does in the section where it goes through a little example, you'll see that it comes out to about 27 newtons per meter. In other words, the bond strength of neighboring atoms is sort of a typical spring constant for a macroscopic spring. It's very interesting. Now let's talk about Young's modulus. If you go look in the, what is it called? It's the Handbook of Chemistry and Physics, and you look for bond strength of bonds in copper or aluminum or some elemental solid, you probably won't find it. What you're going to find is something called Young's modulus. Young's modulus is an intrinsic property of materials that is measured in terms of macroscopic distortions and forces and so on that are exerted on and by materials. If you define the stress to be the force per unit area that's acting on a material, and you define the strain as the change in the length of the material divided by the length, so it's the fractional change in length of the material, Young's modulus is defined as the stress per unit strain. And the interesting thing about that is because the force and the displacement, or the stretch, are sort of proportional to one another, it turns out the stress divided by the strain is independent of the particular macroscopic geometry of the material. It doesn't depend on the length of the wire, it doesn't depend on the cross-sectional area of the wire, it just depends on intrinsic properties of the material itself. In this case, we're talking about copper. So the stress divided by the strain. Now notice that you could rearrange this and turn it into something that looks a lot more like Hooke's law by solving for the force of tension acting in the material, and you'll notice that that's proportional to the elongation, or the change in length of the material. You could think of the change in length as the stretch, and the force that's applied as a sort of tension, and then the fact that they're proportional to one another means that we have a spring-like behavior, but the spring constant is Young's modulus times the cross-sectional area divided by the length. But if you go back and look at our old expression that we cooked up for the spring constant of a piece of wire like this, that the Young's modulus fits in to this expression exactly the same way that the interatomic bond spring constant and the distance between neighboring atoms fits into the expression we worked out using the microscopic properties of the material. And so, in fact, that is Young's modulus. Young's modulus is nothing other than the interatomic spring constant divided by the distance between neighboring atoms. So that's a neat connection. Young's modulus is an intrinsic property of material that's derived by macroscopic displacements and forces, and we just worked out how it depends on the microscopic properties of the material itself. Pretty neat. Let's talk about contact forces. If I set something down on a surface, the surface is going to push back. If you look at that on an atomic scale, what it basically boils down to is that when a force is applied to a material, the interatomic bonds shorten a little bit, and because they're shortening, those interatomic bonds push back with a force that's proportional to the change in the distance between neighboring atoms, and you end up with a contact force. So if you set a brick down, for example, on a table, the table pushes up, the earth pulls down, but on a microscopic scale what happens is the table surface actually deforms, the interatomic bonds are compressed, and those compressed bonds push back up on the brick in order to produce a macroscopic normal force. So there's a microscopic origin to a macroscopic normal force. Another kind of problem we run into a lot in this chapter are situations where things are stationary, and I want to connect that back to the momentum principle. If you have a brick sitting on a table, the net force acting on the brick, if it's just sitting there, must be zero, because the momentum of the brick is constant. And that means that if there are multiple forces acting on the brick, or whatever, that the sum of those forces must be zero. So we're going to deal with some problems in this chapter where you have objects whose momentum is constant, and as soon as you recognize that you're dealing with a constant momentum situation, you can immediately conclude that the sum of the forces acting on that object has to be zero. So the laboratory we're going to do today and the modeling exercise we're going to do on Wednesday deal with spring mass systems. So you've got a mass on a spring with some momentum if it's moving. Its velocity is the rate of change of its position. Let's imagine we're just going to deal with the one-dimensional motion for the moment. We know the rate of change of the momentum is the net force in the x direction, and the momentum principle tells us that that's equal to the mass times the second derivative of position with respect to time. Remember that the velocity is the first derivative of position with respect to time, and therefore the rate of change of the velocity is the second derivative. That's also called the acceleration. So we get that the mass times the acceleration is minus a constant times the displacement. If we set our coordinate system up so that x measures the distance from, or the displacement from equilibrium, then we get an equation that looks something like this. Now the question is, what kind of functions have the behavior that the second derivative of position with respect to time of the function of time is minus a constant times the function again? And we talked about this in class. You guys figured out the answer without my having to tell you. I'll remind you, it turns out to be nothing other than the sines and cosines. So they look something like this. You're familiar with them. I just want to point out that if you assume that the displacement as a function of time goes like a cosine, the velocity goes like a sine, and the acceleration goes like minus omega squared times the cosine back again. So you get an acceleration that's minus omega squared times the displacement. But remember, the original problem was that the second derivative of x with respect to t was minus k over m times x, and so you can identify omega squared with k over m. So that tells us that the omega, that turns out to be a number with units of frequency, 1 over time, it has to be nothing other than the square root of k over m. Finally, I want to point out, not quite finally, we have one more slide after this, but it turns out if there's a disturbance in our model of a chain of atoms, and that disturbance tends to propagate, because if you compress the distance between 1 and 2, 2 pushes on the spring between 2 and 3, and that compresses, and then the string between 3 and 4 compresses, and so on. And by dimensional analysis, we know that the only way to form a velocity out of the properties of the material are to use the distance between atoms, and this thing that we cooked up that has units of 1 over time, it depends only on the interatomic bond strength and the mass of neighboring atoms. So this is not at all any kind of derivation of the wave speed, but it hopefully is a plausible argument that the only thing you can form that has units of velocity that includes the bond strength, the mass of the atom, and the distance between atoms is this particular quantity. And you could have a 2 or a pi or something in there, and it would still be legitimately with the correct units. But it turns out this is, in fact, the correct answer. And if you're interested in how this comes about, we can chat about that on the side. But this does turn out to be correct. And the nice thing is it's fairly intuitive. We know that the omega is the frequency with which an atomic mass would wiggle if it was connected to a spring with the bond strength. So that's kind of how fast things wiggle. And the wiggle propagates at a distance, something like the distance between atoms. So it goes kind of like the wave speed is the distance between atoms, sort of like divided by the time of one wiggle. That's not exactly right, but that's sort of intuitively what's going on. Okay. Okay, sorry about that. The last bit I want to share with you guys is the idea of static and kinetic friction. Let's say I have a block that's not sliding. It's sitting at rest on a surface, and I know that the Earth is going to pull down on the block, and I know the surface is going to push up on the block. And because the block is not accelerating, it has no rate of change in momentum, those two forces are going to cancel. And then I apply a force. It turns out if the force I apply is not too big, the material will resist permitting that thing to move. You can imagine on a microscopic scale you're trying to push these atoms around and they're going to push back. And that pushback is called friction. And in this case it's called static friction because the thing is not actually sliding. The force of static friction is whatever it takes to keep the thing from sliding, but there's an upper limit to what that can be. And so the relationship we're going to learn in this class is that the force of static friction is less than or equal to a number times the normal force. The normal force is the force, the compression force pushing back up on the block because it's compressing the mattress. Okay, it's like I think of it as a mattress force. And the frictional force is a sideways, don't slide on me force that prevents excuse me, the block from sliding. And the point is there's a maximum value the force of static friction can have, and it turns out to be proportional to the normal force. The greater the normal force is, the greater force you need, the greater force the surface can produce to prevent sliding. And the proportionality constant between that maximum force the surface can produce and the normal force is called the coefficient of static friction. It's that mu sub s thing down there at the bottom. Next, if we have an object that is sliding, okay, it's sliding along with some non-zero velocity. Again, we have the weight. Again, we have the normal force. We could have an applied force, or we might not have an applied force. But the point is, the thing is sliding to the right in this picture. The velocity is to the right. So now there's an opposing force, and it's called the force of kinetic friction. And there's no inequality here. Experimentally, it's found that the force is proportional to the normal force. And the coefficient of kinetic friction is that constant of proportionality. And that's the whole thing for today. I'm sorry it was a little bit rushed, but I had to get it out, and so here it is. Hope you enjoy. Welcome back, guys. It's time for Chapter 5, the rate of change of momentum. So let's go ahead and get started. I have to first, we're going to work some theoretical ideas, and then we'll talk about some practical strategies. So suppose a particle moves along a curved path, something like this. It could be speeding up and slowing down, and also changing its direction of motion. And the question is, how do we analyze that? So the first thing is to identify a point in the motion that you want to pick as a kind of reference where you want to analyze what's going on. So let's say we decide to pick a point, something like this, and we need to set up a framework, a kind of a reference frame, I guess, to analyze the motion. But it turns out it's useful to consider the net force and the momentum as a starting point for a frame of reference, because you can always resolve the net force into components perpendicular to the momentum and parallel to it. So the way to think of this is the net force and the momentum vector form a plane, and in that plane you can resolve the net force into components perpendicular to the momentum and parallel to it. And the reason we're going to do that is because both mathematically and physically, these two components of the net force have a very different effect on the momentum. And we want to understand that effect, and in order to analyze the problem mathematically, it turns out that resolving the net force vector in this way is useful. So the perpendicular component of the net force is proportional to the perpendicular component of the rate of change of momentum, and the parallel component of the net force is equal to the parallel component of the rate of change of momentum. That makes sense? Let me show you a little demo, VPython demo, to see how that works. Okay, so here's a picture of a particle under the influence of a force, and let's just watch what happens. The force is just varying in time in some complicated way, and the resulting motion of the particle is some complicated curve, and you can see that it looks difficult, but we want to try to analyze it. So the idea is, first of all, let's look at the momentum. So let's replay the movie now, but with the momentum drawn in. Now the momentum is a blue vector that always points in the direction of motion. And you can see that at every point in time, the momentum and the net force form a plane. In this case, it's the plane of the screen. And we want to analyze the motion by decomposing the force into components parallel to and perpendicular to the momentum. So let's see what that looks like. Now in this movie, you've got the momentum here. The net force is the big green arrow, and the components of the momentum perpendicular to and parallel to the momentum, the components of the net force perpendicular to and parallel to the momentum show up. And so you get a sense of how the thing is going to go. Notice that as the momentum changes, and the net force changes relative to the momentum, the components parallel to and perpendicular to the momentum can change sign. So here, for example, the net force has a component in the same direction as the momentum, so this guy is making the momentum grow in magnitude, and this guy, the perpendicular component, we're going to find out, changes the direction, changes the direction of the momentum, and you can see that as a result, the momentum direction is going down, and it's getting longer. But at this point, the component parallel to the momentum is now in the opposite direction, so it's going to start bringing down the magnitude of the momentum. But the thing is still changing the direction in the same way, so you get a curved trajectory that moves down. So that's kind of how it works. As the relative direction, now the momentum's getting bigger, now the momentum's getting smaller, and so on. But the direction of curvature depends on that perpendicular component. The magnitude of the blue arrow depends only on the component of the momentum that points in this parallel to the momentum. So let's look at that again. But so here it's curving up. Now it's going to start curving down because of that perpendicular component. It's going to curve down, down, down. And then here it switches and starts curving the other way because the perpendicular component is now pointing in the other direction, and so on. But as far as magnitude of momentum goes, we only have to look at the parallel component. So here the parallel component is in the same direction, it's speeding up. Now it's slowing down, slowing down, now speeding up again. And now it's slowing down again. So the parallel component changes the magnitude, the perpendicular component changes the curvature. And that's the way that works. Okay, let's talk about the actual components of the rate of change of momentum. Suppose you have an initial momentum vector pointing in some way, and then over the course of some period of time, the momentum changes by an amount delta p. Now I'm drawing the picture big with a large change in momentum in order to clarify the components of the change in momentum. But in the end, we take we take the limit as the time interval becomes infinitesimal, which means that these relationships that we develop are going to become exact. Let's see how that works. So first of all, there's the parallel component of the change in momentum. Notice that the parallel component of the change in momentum has the primary effect of changing the magnitude of the momentum vector, and the perpendicular component of the change in momentum has the primary effect of changing the direction of the momentum vector. Now I'm interested in rates of change, so what I want to do is to divide each of these by the corresponding change in time, and then notice that the rate of change, the perpendicular component of the rate of change of the momentum, is nothing other than this ratio, delta p perpendicular divided by delta t, and the limit that delta t becomes very tiny. And also, the parallel component of the rate of change of momentum is nothing other than delta p parallel divided by delta t, and the limit as delta t becomes very small. Now let's look at this a little more mathematically. If we define the momentum as the product of its magnitude and a unit vector that points in the direction of the momentum, let's call that p hat, we can write the momentum vector as the magnitude p times p hat. Magnitude p, remember, is a scalar. If I take the derivative of the momentum vector with respect to time and apply the product rule to this product, I get that the rate of change of the momentum vector is the rate of change of the magnitude of the momentum vector times a unit vector that points in the direction of the momentum. That's the parallel component, and so we can think of that as dp dt parallel. How do I know it's parallel? Well, it points in the p hat direction, so it's got to be parallel to the current momentum. And then the other piece, which is the magnitude of the momentum times the rate of change of p hat, has got to be the perpendicular component. Now, we'll see in a moment geometrically how dp hat dt happens to point perpendicular to p hat. But suffice it to say that dp hat dt and p hat are perpendicular to one another. So looking at this again, if I have a momentum vector that points in a certain direction, p hat is the unit vector that points in the same direction. Delta p is some small change in the momentum. Delta p parallel, which is the magnitude of delta p, or the change in the magnitude of the momentum vector, times the unit vector that points in the momentum direction. That's delta p parallel. Delta p perpendicular is the magnitude of the momentum times the change in p hat. And of course, again, I can divide these guys by delta t, and you can see the connection between dp dt parallel, dp dt perpendicular, and the rate of change of the magnitude of the momentum and the rate of change of the direction, the p hat vector. All right, let's keep pushing on this. So I went ahead and put the mathematical definitions of dp dt parallel and dp dt perpendicular back at the top. I'd like to look at this thing geometrically. So what I've got here in this picture is a particle moving along a curve with a radius of curvature capital R. And we've got p initial hat and p final hat. Remember, these guys are unit vectors, so they have exactly the same magnitude. And notice that the change in p hat is a small vector, and in the limit that time interval becomes small, you can see that this small vector, delta p hat, is going to be perpendicular to p hat. Notice that there's an angle theta. Theta is the angle through which the thing has gone. It's both an angle in real space and an angle between the two p hat vectors. It's the same angle because as the particle moves along the curve, both the r vectors that go from the center of the circle out to the position of the particle and the p hat vectors turn through the same angle since they're perpendicular to one another. And you can see that therefore we have two similar triangles. There's the p hat triangle that has delta p hat as the small side and p hat initial and p hat final as the long sides. and then the space triangle, the actual physical space triangle, which has the distance traveled by the particle. That's the magnitude of the velocity times the change in time. And it's got the radius of curvature of the curve as the long side. Now, if these are similar triangles, which they must be, because theta is the same for both, and they're both basically isosceles triangles, right? So it means that delta p hat over the magnitude of p hat must be the same thing as v delta t divided by r. Now the magnitude of p hat is 1 because p hat is by definition a unit vector. And so I can simplify this thing and take the limit as delta t goes to 0. And what I get is that dp hat dt is a vector perpendicular to p hat with a magnitude of v over r. Because you can see that the delta t went away because I turned it into dt. So what that says is that the magnitude of dp hat dt is always just the velocity of the particle divided by the radius of curvature. And there's nothing specific to low speeds about this. So this is actually even true at relativistic velocities. Now let's take that and put it back in. First of all, I want to remind you of the momentum principle, that dp dt is the net force. You can think of resolving the net force into the parallel and perpendicular components of the force. So for example, if you have some comet moving around a star, the net force, of course, is gravitational, and you can always resolve the net force into the parallel and perpendicular components, parallel and perpendicular to the instantaneous momentum of the comet. The idea is that the parallel component is the rate of change of the magnitude of the momentum times p hat. The perpendicular component is the magnitude of the momentum times the rate of change of p hat. But we just worked out that the magnitude of the rate of change of p hat is v over r. And so we can write out that the perpendicular component of the force is the magnitude of the momentum times the ratio v over r. Now, the one thing I haven't done here is to specify the direction of the perpendicular component, but it always points toward the center of curvature. If you go back to the geometry from the previous slide, you can see that it always has to point toward the center of curvature of the curve along which the particle is moving. So I'll just say in vague terms, toward the center. Okay. Now, what do we mean by r? If a particle moves along a curve, if I imagine analyzing the motion at a particular point, r, there's no circle in this picture. The particle is just moving along some curve. But r is the radius of curvature of the circle that matches the curvature of the curve at the point in question where you're actually doing the analysis. So that's called the kissing circle because it matches the curvature of the curve like a kiss, and the radius of curvature of that circle is the same as the radius of curvature of the curve at that point. All right, very good. So now, the question is, that's all very theoretical. We've got some theoretical ammunition here to solve problems. But the question is, how do we actually solve problems? So I've got a few hints for you about how to do that. First of all, I want you to watch the Free Body Diagram podcast that I posted to ACE. It goes through in detail explaining how to draw free body diagrams, how to identify forces, and things like that. And it goes through two examples in detail where there is changing momentum. Now, they are both, these particular examples in the Free Body Diagram podcast, are both straight line motion. There is no curved motion. But we'll get a lot of experience with motion along a curve in this chapter. But there are both good examples of situations where there is a rate of change of momentum, at least. The one thing is, I created that podcast for a course that used the more traditional language. And so where the podcast says Newton's second law, I want you to think momentum principle. The podcast uses mass times acceleration. We use rate of change of momentum. It's the same thing at low speed. Rate of change in momentum, it turns out, is actually more general because it also works even at relativistic speeds. But for the purposes of a lot of the examples we'll be doing in this chapter, you don't need to worry about the relativistic situation very often. There's another thing that shows up in the podcast that's relevant, and it's the fact that when one object pushes on another object, the second object pushes back with an equal and opposite force. We know that as reciprocity, but the traditional physics curriculum calls that Newton's third law. It is Newton's third law. It's just that in this textbook, the textbook we're using, that's called the reciprocity principle. So if you just make those substitutions, everything else is okay. So I thought the easiest way to show you how to do this was to actually work out a complete example. This is an example of pulling a loaded sled with a total mass of 40 kilograms at a constant speed in the x direction, using a rope that's at an angle with the coefficient of friction between the snow and the sled. And the question is, what's the tension in the rope? So the idea is to draw a free body diagram. So there's my sled. You don't have to be an artist. You just have to have a diagram that indicates what the thing is. There's the snow, and then we have to start identifying forces. So we've got a tension. That's the force of the rope on the sled acting at an angle of 35 degrees. Then we've got the earth pulling down on the sled. We can call that the weight force of the earth pulling down on the sled. Then we've got the snow pushing up on the sled, or the ground pushing up on the sled. Sometimes that might be called a normal force. It's kind of the mattress force I always talk about. It's the squishing of the atoms. And then there's the friction between the ground and the sled, and the friction is going to oppose the motion. Now, I'm assuming there's a constant velocity to the right in the same direction as the pull of the rope. Excuse me. But the snow is going to oppose that with a force that goes to the left. So the first thing to do after you've identified all the forces and drawn the free body diagram is to write out the momentum principle. And the momentum principle says the sum of all those forces, the normal force plus the frictional force plus the tension plus the weight, has to equal the rate of change of the momentum of the sled. Now in this particular example, the rate of change of the momentum, of course, is 0 because the sled is moving it with a constant speed in a straight line. In problems where that is not true, where the speed is increasing or decreasing, or where the motion is not in a straight line, then the rate of change of momentum is not going to be 0. And you're going to have to figure out what it is based on what's happening in the problem. But in this case, it's going to turn out to be 0. Now, after we've written out the momentum principle in vector form, I like you to write it out, write each component as a separate equation. So let's look at the x components, the horizontal components of these forces. First of all, there's the x component of the normal force. There's the x component of the frictional force. There's the x component of the tension, and the x component of the weight. Those have to equal the x component of the rate of change in momentum. But you can see the normal force points straight up. So that means that the x component of the normal force is 0. Likewise, the weight points straight down, so the x component of the weight is 0. And finally, the momentum has no rate of change in either x or y direction, so its x component is definitely 0. We can also put in that the frictional force has a negative x component, so I can just write that as minus f, where f is the magnitude of the frictional force. And the tension is directed at an angle, so that means the x component of the tension is the magnitude of the tension times the cosine of 35 degrees. And those guys have to add up to 0, so that's one equation. Now let's look at the y components. Again, I have the y component of the normal force, the y component of the frictional force, the y component of the tension, the y component of the weight is equal to the y component of the rate of change of momentum. Now, in this example, in this component equation, the frictional force has no y component, and the rate of change of momentum is still 0, even in the y direction and in the x direction. So I can get rid of those right out of the box. The normal force, however, is not 0, and it has a positive y component. The tension is not 0, and its y component is t times the sine of 35, or the way the authors in the book do it is the cosine of 90 minus 35, which is the same thing as the sine of 35. And of course, there's the weight, which has a negative y component of mg. And those guys have to add up to 0. So let's reorganize here a little bit. Okay, so what about that frictional force? Now we know that the magnitude of the frictional force is equal to the coefficient of friction times the normal force. This is for kinetic sliding friction, so it's the coefficient of kinetic friction. But because the sled is moving with a constant velocity, there's no ambiguity here. The thing is definitely sliding. So we can simply write F is equal to mu times n. I can also solve the equation on the right for n, and I get n is mg minus t sine 35. So substituting in the friction and solving for n on the right, notice I've got two equations, each with two unknowns, n and t. But the standard strategy for dealing with a situation like that would be to simply solve one equation for one unknown and substitute into the other. So I'll do exactly that. I'll take the expression for n on the right and substitute for n on the left. And now I have a single equation with t as the only unknown. I can expand the binomial on the left, collect terms with factors of t, and then factor the t out. I end up with something like this. And then I can just solve for the tension. And you can see that it comes out as 84 newtons. And this is also done in the textbook, in the example. You can take a look at that. But that's how it's done. So the idea is you make a free body diagram, you write out the momentum principle in vector form, you break it into components, and then you solve for the variables that you're left with. And that's the end. We'll see you guys next time. Hey guys, welcome back. It's time for chapter 6. This is about the energy principle. And first we need to know what the heck the energy principle is. It's that the change in the energy of the system is equal to the work done on the system by the surroundings plus the thermal energy transferred from the surroundings to the system. Let's look at that. The change in the energy of the system is going to be the change in all types of energy that are considered part of the system. So remember, in any problem, you've got to separate the system and the surroundings. And the energy is something you can calculate if you know the position and velocities of all the particles in the system. And that's a lot of what this chapter is about, so we'll get into how you actually do that, but that's the idea. Work is something we need to define, but the point is the surroundings can do work on the system, and doing work changes the energy of the system. So that's the idea of that. And finally, although we're not going to do much with this in chapter 6, it's worthwhile to point out that you can also change the energy of the system by having thermal energy flow from the surroundings to the system due to temperature differences between the system and the surroundings. So that's something we'll hit more a little bit later in the course, but I wanted to make sure we got it in now since it's an important part of the energy principle. The simplest case is if you have a single particle. If you have a single particle that's not interacting with the, well, no. If you have a single particle, and that's all there is that's in the system, everything else is in the surroundings, then the energy is easy to compute. It's just gamma mc squared. You can see if the particle is at rest, gamma is equal to 1, and you get the rest energy, mc squared. If you have a particle in motion, then in addition to the rest energy, you get kinetic energy, which is the energy a particle has by virtue of the fact that it's moving, and you can see that that just turns out to be gamma minus 1 times mc squared. Kinetic energy, as I said, is the energy a particle has because it's moving. This purely as a consequence of its motion. So for example, if you have a proton that's moving with a gamma of 4, its energy is going to be 4 times its rest energy, 4 mc squared. But 3/4 of that, 75% of it, is going to be kinetic energy. So its kinetic energy is 3 times its rest energy. And you can see that as the speed becomes low, you can use a sort of binomial expansion of gamma. Gamma turns out to be 1 plus a half of v over c squared in the low speed limit. And in that limit, you can then see that the kinetic energy is just 1/2 mv squared. If you've taken physics before, this is probably the definition of kinetic energy you used. And this is perfectly fine as long as the speed doesn't get close to the speed of light. And you can see the total energy then is the rest energy plus 1/2 mv squared. Now, what if you have, if you want to relate energy and momentum, you know that the energy is gamma mc squared, but the momentum is gamma times mv. So you can see that momentum, let's see, how would we do it? Momentum times c squared plus the rest energy squared is equal to the total energy squared. If you look at this expression and also look at the expression before, you can convince yourself that this is right. And then you can find a new way to compute the kinetic energy, which is the squared momentum over gamma plus 1 times the mass. In the low speed limit, this reduces to p squared over 2m, but it's p squared over gamma plus 1m in general. So that's the way that works. Now, what about work? How do we compute work? Work is something you calculate based on force and motion. So if you have a force that acts while a particle is displaced by a distance displacement delta r, the work is simply the dot product of the force vector and the displacement vector. And I'm going to define dot product as a way to multiply two vectors together, where you take the products of the corresponding components and add the products together to get the result in dot product. So we've got the x component of f times the x component of displacement plus the y component of f times the y component of the displacement plus the z component of f times the z component of the displacement. So literally, if we have a force, for example, of 3, 3, 0, and you have a displacement of 5, 0, 0, to calculate the work, you'd take 3 times 5 plus 3 times 0 plus 0 times 0, and you get 15 Newton meters of work. We're going to define a Newton meter to be a joule, so that's easy enough to do. Now, what is it with the dot product? The neat thing about the dot product is that the result of computing the dot product is independent of the coordinate system that you pick. And that means that we can pick any coordinate system we like. So if we happen to pick a coordinate system where one of the vectors points in the x direction of our chosen coordinate system, then you can see that the x component of that vector is going to be non-zero, but all the other components will be 0. The x component of the other vector, a, will be the magnitude of a times the cosine of theta. And so one immediate consequence of that is that, that one way to compute the dot product of two vectors is to take the product of their magnitudes times the cosine of the angle between the two. So what that boils down to is there's two ways to calculate dot products. You can take the product of the components and add, or you can take the magnitude of the two vectors multiplied by the cosine of the angle between the two vectors. Well, now what happens if I have a non-constant force? Well, the answer there is I break the motion up into pieces. I can calculate the work done along the first piece, then switch to the different force, calculate the work done along the second piece, and add the two works together. So the short answer is you break the path up into chunks, and each chunk you take the force acting on that during that chunk, dot it into the displacement for that chunk. And you do that as many times as you have to get an accurate estimate of the work. If the force varies continuously, you can take the limit as the size of the chunks goes to 0, and then the work becomes an integral. And we did an example of that in class on Friday, but that's sort of the mathematics of how that goes. And that brings up the notion of potential energy. So what the heck is potential energy? Potential energy is a kind of energy that you need in order to take into account interactions between multiple particles in the system. So if I include more than one particle in the system, and they do work on one another, the potential energy keeps track of that work. So here's the idea. Let's say I
I have a system where the kinetic energy changes, and part of that comes from work done internal to the system, and part of it comes from work on the system by the surroundings. The notion is I define the internal work done as the negative of the change in the potential energy. In other words, I treat changes in work done by particles inside the system as being a change in internal energy, and then I move that delta U to the other side of the equal sign, because I'm going to incorporate that into the energy of the system, and that then becomes the work done on the system by the surroundings. In other words, I'm just shifting work internal to the left side of the equal sign. It'll then be minus work internal, and I'm defining minus work internal to be the change in the potential energy. So basically, potential energy is just a way to keep track of work done by particles that are in the system on each other. Okay? So that means the total energy is now going to become the total rest energy of all the particles, plus the total kinetic energy of all the particles in the system, plus the potential energy, the interaction energy between all the pairs of particles in the system. So I've tried to write this out. It's the potential energy between particle 1 and particle 2, between particle 1 and particle 3, particle 1 and particle 4, dot, 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 plus the interaction energy between particle 2 and particle 1, plus particle 2 and particle 3, and dot, dot, dot. And so you enumerate all the pairs of particles in the system, and you add up their potential energy of interaction. And the general rule is that particles don't have interactions with themselves, so you don't have a potential energy of a particle with itself. Okay, so you can kind of think of potential energy as stored work. So the idea is, in order to get the system the way it is now, the surroundings had to do some work, or some work had to be done, I guess, to bring particles together or set them up the way they are. And so you could sort of think of potential energy as the work done to get things set up. And it's sort of the work needed to put things in the configuration that they happen to be in at this moment. And so it's kind of a stored work. It's a stored energy that you can get back by allowing the particles to relax to some other lower energy configuration that energy is available to do work in some fashion. And the other thing is, it's often convenient to define potential energy so that it's zero when particles are separated an infinite distance. Now, we sometimes violate this for convenience. So for example, when we define the potential energy of an elastic spring, say, or if we're working always near the surface of the Earth, it's convenient to just say, well, if we're working near the surface of the Earth, we're going to pick some other zero of potential energy. But I want to point out when we get to the expressions for potential energy that a lot of the fundamental forces produce potential energies that go to zero when the particles have infinite separation. And we'll see how that works here in a moment. So let's look at some examples. If you calculate the work needed to stretch a spring from equilibrium, it turns out to be 1/2 ks squared. Now that's relative to the unstretched condition of the spring. So if the spring is unstretched, you could think of it as having a baseline potential energy. And then if you stretch it relative to that unstretched condition, it takes an amount of work, 1/2 ks squared, and so its potential energy in that stretched condition will be, or compressed condition, will be 1/2 ks squared. Now, if you go back to my original statement that the potential energy is zero only when particles are at infinite separation, I could take the atoms of the spring and send them all out to infinity, and that would give me a true zero of potential energy. But that's not really super convenient if all I'm interested in is what happens to the potential energy of the spring relative to the condition when it's just sitting there unstretched. So I put a relative in parentheses here to point out that this one does not go to zero when the atoms are in infinity, but it is 0 when the spring is unstretched. So that's and that's convenient for like using springs in the laboratory and that sort of thing. The gravitational potential energy between two objects, this one does go to 0 at infinity. You can see if I put in the distance between the two objects is infinity, this potential energy goes to 0. So this is relative to infinite separation. Then we've got a electrical potential energy. This is sort of similar to the gravitational potential energy, except using Coulomb's law. This one, as you can see, also goes to 0 at infinity. And if we're using gravitational potential energy only near the Earth's surface, we don't go far from the Earth's surface, we can use the approximate relationship, mgy, where y is 0 at some relative 0 of the potential energy. So we can, what it boils down to is you can pick the 0 of potential energy wherever you like. Many of the formulas that we use choose the 0 at infinite separation, but sometimes it's convenient to pick a different 0, like for the example of using the elastic potential energy of a spring or the gravitational potential energy near the Earth's surface. It's awkward to always refer to r equals infinity when you're just talking about a mass that's going from the tabletop to the floor, or something like that. So by doing some worked examples in class, I hope you'll get some experience with this and you'll see what I'm talking about. The last thing I want to discuss is the notion of an energy diagram. An energy diagram is just an easy way to sketch out what's going on with the energy. So here's an example where two stars are falling together, and we want to look at the kinetic energy, the potential energy, and the total of kinetic and potential energy as a function of the distance between the stars. Now, notice this is the horizontal axis here is distance, so as the stars get closer together, we're going to move from right to left, and you can see that the potential energy falls, the kinetic energy increases, but the total of the two, the sum of the two, kinetic plus potential energy, remains constant. And what that means is, because the stars are falling in toward one another, the surroundings is not interacting with the two stars, so no work is being done by the surroundings. And that means that the change in the energy of the two-star system is constant. That means that if the potential energy of the two-star system goes down, then the kinetic energy of the two-star system has to go up, keeping the sum of kinetic and potential energy constant. That's kind of the idea. Let's look at another one. Here's one where two protons are falling together. And we're going to graph the same thing, the kinetic plus potential energy. The difference here is that as the proton separation increases, the potential energy decreases. Remember, in the gravitational case, when the separation increased, the potential energy increased. Here, if the separation increases, the potential energy decreases. So the kinetic energy has an opposite relationship. As the two protons approach one another, the potential energy increases, but the kinetic energy decreases. That's the idea. So they slow down as they get closer together, and that's consistent with a repulsive force. Once again, if the two protons don't significantly interact with the surroundings, then the sum of the kinetic energy plus the potential energy is going to remain constant. Same idea. And what about a bound system? That would be like the Earth going around the Sun, or an electron going around a proton, or something like that. In that case, what you have is kinetic plus potential is less than 0, and this is for an attractive case. The kinetic plus potential energy are less than 0, and what that means is as the separation between the two objects increases, the kinetic energy is going to decrease, but the kinetic energy cannot decrease below 0. So what that means is there's a maximum separation that these guys can have, because if you increase the separation beyond the point where the kinetic energy can be positive, the thing will turn around and go back. So you end up with what's called a bound state, and the point at which the kinetic energy goes to 0 is called a turning point of the system. So we'll see this with oppositely charged particles. We can see this with gravitational systems, and we can also see it with things like masses connected to springs. So we'll look at examples like that and get some experience with those things. So The last thing I want to say is that to develop a little intuition about what's going on, you might imagine that if you have a potential energy graph as a function of position, and you want to know what's going to happen to the system at different values of r in this case, for example, or different values of position, one way to think about it is if I just imagine setting down a marble on this surface, where the surface is sloped downward to the right, the particle is going to move to the right. It's going to experience a force to the right. If I put it down in a region where the slope is upward to the right, the particle, if I set it down in that place, you can imagine, it's going to experience a force to the left. And if I put it at a point where the slope is 0, then it will have no tendency to go right or left. If the curvature is upward at that point, it'll be a minimum, and that means the particle will sit there stably. If the curvature is downward and there's no slope, that means it's an unstable equilibrium. If I put the particle there, and any small change will cause it to either go to the right or to the left. So that's a crude sort of visual technique to kind of get a sense of what's going on. It's not exactly right, because if you actually stick a marble on a hill, it's more complicated, because the thing's going to move in 2 dimensions first of all, and it's going to roll and do other things that we haven't really even gotten to yet. But just as a kind of a gut feeling of what's going to happen to something that's in a potential of a particular shape, you can use that as a starting point at least. I also want to point out that there's a direct connection between the slope of the potential energy function and the force. And you can see it comes back to the definition of work and what potential energy means. But basically the negative slope of the potential energy is the force. And we're going to use that in some of the examples. I lied. I did have one other thing I wanted to discuss, and that's the notion of mass. So if you have a multiple particle system, the total energy is going to be the sum of the rest energy. So let's say we have a bunch of identical particles, so it's n times the rest energy of one particle, plus the sum of the kinetic energies of all the particles, plus the sum of all the potential energies of interaction of all the particles. That's going to be the energy. But we also know that Einstein has this relationship that E equals mc squared. Now that's the rest energy of a multiparticle system. So if I have a multiple particle system where the total momentum of the entire system is 0, that means that the velocity of the system as a whole is 0. So the system as a whole is at rest. So that would mean it would have its rest energy. And the point is that Einstein tells us that the mass of the system times c squared is its energy. But we also know the energy can be expressed in this other, more complicated way, involving the rest energies of the individual constituents of the system, plus their kinetic energies, plus their potential energy of interactions. And the question is, which of these is right? And the answer is, they're both right. They are both right. They're just different ways to look at the same thing. So when you say a particle has a certain rest energy, but in reality that particle has constituents, subparticles that make it up, then that rest energy that you're using is actually includes all the different flavors of energy that are going on in the system of that particle. Anyway, that is truly the end. We'll see you guys next time. Hey guys, welcome back. It's time for Chapter 7, Internal Energy. I want to begin by reviewing a little bit about elastic potential energy. If you start with Hooke's law, which says that if you compress or stretch a spring, you get a force that goes like minus the amount of compression or stretch times a constant, and you go to compute the potential energy stored in the spring, that would be the integral of minus the force dotted into the displacement. Remember, the force is minus the derivative of the potential energy, so the potential energy is minus the integral of the force. You could think of it that way. You end up with a potential energy that's related to the stretch, and it looks like a quadratic. Now this is only valid, the quadratic part is only valid for very small amounts of stretch, relatively tiny compressions or stretches.
but it's a good model as long as the stretch isn't too much. You can relate this to the bond strength of two atoms that are near one another. It turns out that for small amounts of stretch, the work needed to separate or push the atoms together also looks like a quadratic for exactly the same reason. Now, folks who are interested in this use a slightly more sophisticated potential to model actual neutral atom interactions. It's called the Morse potential, and it does a pretty good job of approximating the potential energy as a function of separation for two neutral atoms. It kind of looks like this. It has a minimum. That's the equilibrium separation between the two atoms. And if you try to separate the atoms farther, you have to do work, so the potential energy goes up. If you try to push them closer together, you have to do work that way as well, so the potential energy goes up. So it has a vague resemblance to the quadratic potential. In fact, at the minimum, the resemblance is quite good, and that's basically what we're going to do, is assume that we're close to the minimum, and so we can use the quadratic approximation both for two atoms that are interacting with one another and also for a collection of atoms, because remember, a collection of atoms, kind of like a collection of springs, also has the Hooke's law behavior. Now, in this chapter, we're also going to be dealing with thermal energy, and thermal energy is really just microscopic kinetic and potential energy, and the average kinetic energy and potential energy per atom, I'm being vague here because it's not exactly right. We'll get a better definition of temperature later, but the temperature is kind of like the average kinetic energy per atom or per molecule. The specific heat capacity is a proportionality constant between the change in temperature and an amount of thermal energy needed to produce that change in temperature. Specific heat capacity is heat capacity per unit mass. So to get the change in the amount of thermal energy needed to produce a change in temperature, you take the mass of the thing times the specific heat capacity times the change in temperature, and you get the thermal energy needed to produce that change in temperature. If you followed that, you'll know that the specific heat capacity has to have units of joules per gram or per kilogram, and then per degree Kelvin or per degree Celsius. So that's the idea of specific heat capacity. We'll work a problem here in a minute that shows kind of how that works. Also, we're going to add another term to our energy principle, which we talked about in class, but I just want to point it out here. It has to do with energy transfer due to temperature difference. If there's a temperature difference between the system and the surroundings, you'll get a thermal energy transfer, and that thermal energy transfer corresponds to a change in temperature. So as the temperature goes up, and this is the formula for specific heat capacity, mass, change in temperature, and the amount of thermal energy needed to do that. So one other new idea in this chapter is the concept of power. Power is the rate at which energy changes or flows. Energy moves from place to place or from form to form via work and or heat transfer or thermal energy transfer. I'm going to try to use heat as a verb whenever I can, but I'll probably forget sometimes and say heat as a noun. But basically, when thermal energy goes from place to place, then that can be thought of as a Q. In our equation, delta E equals work plus Q. And power is simply the rate at which energy flows, so the rate in time. So a watt is a new unit, which is 1 joule every second, and that's a unit of power. So finally, or at least not finally, but next is the idea of dissipation. So dissipation is a process, usually it's involving work of some kind, in which energy changes from organized macroscopic energy into microscopic potential and kinetic energy, usually associated with thermal energy. So friction is an example, where if you've got sliding friction, where two objects slide against one another, the interface between those two objects generally gets warmer, increases its temperature because friction involves a lot of little tiny motions, and those little tiny motions correspond to microscopic kinetic and potential energy, and we interpret that as thermal energy, which basically involves changes of temperature. Air friction is another example of dissipation, which results in change in temperature, and another case where you end up getting dissipation and changes in temperature is electrical resistance, which we'll talk more about next semester. So we have a couple of approximate models that we use for friction and drag. There's the air drag, quadratic air drag formula we'll be using in the lab on Monday, where we drop the coffee filters and estimate the air drag force acting on the coffee filters. We're going to find that it's proportional to their velocity squared, for reasons that we may get a chance to talk about on Monday. But also there's sliding friction when two objects slide against one another. We've run into that before, and so you should be familiar with it. And of course there's static friction, where two objects are in contact but they're not actually sliding. So there's a frictional force associated with that contact, and but there's no work done because things aren't actually moving or sliding. There's no dissipative work done. So here was one of the warm-up problems that we had today, and people were so confused by it that I thought it would be worth actually working through it step by step. And so the idea is you have a block of aluminum that slides to rest on a rough surface, and we want to compute the increase in temperature of the block of aluminum. So the way I approached this was to do the problem twice. First, start with the energy principle and choose to make the block the system, where by the block I mean I'm going to ignore the internal energy of the block. I'm just going to keep track of the kinetic energy and nothing else. So the change in the energy that I'm going to bother to keep track of is simply the change in kinetic energy, and the work done by the surroundings will be equal to the change in the kinetic energy. Now the block and the rest of the surroundings are at the same temperature, so there's no Q at this point. And we simply write down that the change in the kinetic energy is equal to the work done by the surroundings. We can put in the numbers from the problem to get the work done by the surroundings. It turns out to be -0.4 of a joule. So that's one approach to the problem. Of course, that doesn't tell us anything about the change in temperature of the block. So let's work the problem again, but this time let's assume that the block and the floor and the surface and everything with it are the system, and the surroundings are everything else. But the point is, the surroundings don't exert any forces on the block that aren't negligible, and so the work done by the surroundings is going to be 0. And the change in the energy of the block has got to be the change in the energy of the system has got to be 0. Remember, though, now the system is the block plus the floor, and the internal energy of the block is going to have to be included. So the idea is the change in kinetic energy we know is -0.4 joules. What else goes in there? And the answer is it's got to be the thermal energy that gets generated and that winds up in the block and the floor. The sum of those two guys has to be 0. Well, we know the change in kinetic energy is -0.4 joules. That means the change in the thermal energy has to be +0.4 joules. And if you go back and look at the text of the problem, you'll remember that I said that half of the generated thermal energy goes into the block. So that means that the change in thermal energy of the block itself is 0.2 of a joule. We can presume that the remainder of the thermal energy went into the floor, went into the surface. The surface of the floor warmed up a little bit. But the idea is that mc delta T is 0.2 joules. I can use that relationship, that the thermal energy produces a change in temperature of the block, to solve for the change in temperature, and it works out to be about 1/1000th of a degree Kelvin. So that's kind of how you think about problems like this. Let's look at another one. A vertical spring with a certain spring constant is compressed,
and a 50 gram mass, a 0.05 kilogram mass, is placed on top of the spring and released. How high will the mass rise before it reaches its maximum height? That's the question. So let's see what happens. We release the spring, the mass goes up, reaches some maximum height. S is the amount the spring is stretched. H is the change in the y coordinate of the ball. And how do we figure out how this works? Well, again, we use the energy principle. Again, we let the system be the ball plus the spring plus the earth. And the reason for doing that is that then the work done on the system by the surroundings is 0, and we simply have that the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy, all that has to add up to 0. Now at the beginning the ball's at rest, and at the end the ball's at rest, so the change in kinetic energy has got to be 0. The change in the gravitational potential energy is, in the relative gravitational potential energy, is mgh, right? And the change in the elastic potential energy, again, it's a relative elastic potential energy since we set it to 0 when s is equal to 0, then it turns out to be negative 1/2 ks squared. So the idea is the gravitational potential energy is increasing by mgh, the elastic potential energy is decreasing by 1/2 ks squared, and so the sum of those two has to be 0 because there's no work being done by the surroundings. So what you can do then is, I guess we'll watch it again here. What you can do then is solve that for the height, and it turns out the height is ks squared over 2mg. You can plug in the numbers, and you get 0.41 meters. So that's kind of how you can solve problems where it's all springs and gravity and kinetic energy and stuff like that, and you can apply the energy principle in a lot of cases like this. So I want you to try this out yourself, check it, and make sure you can do it, and we'll see you guys next time. Hey guys, welcome to Chapter 8 on quantization. We're going to talk about the way matter and energy are quantized on a microscopic scale. And so let's talk about the fact that energy is chunky. First of all, electromagnetic energy always comes in chunks called photons. You can have 1 photon or 2 photons or 0 photons, but you can never have 3 1/4 photons or 6.87 photons. Photons always come in whole number amounts. And then kinetic and potential energy of some systems is quantized. So an electron that's free to move in empty space is not restricted to have any particular amount of kinetic or potential energy. But if an electron or any particle finds itself bound in a system where it can't get out, it's constrained to live in a certain region of space, then it turns out its kinetic and potential energies have to add up to only specific, well-defined amounts. Otherwise, it doesn't work. So we'll see how that turns out in the hydrogen atom, for example, or in other situations. And of course, you recognize that matter is already chunky in the sense that it comes in particles of definite mass and charge and so on, electrons and protons and neutrons and so on. But we're going to find out that its behavior has sort of chunky aspects as well. So let's go ahead and get started, and I think with some examples you'll see what I'm talking about. So the first example is the hydrogen atom. It's an electron and a proton bound together. Because they're bound, it turns out the total kinetic and potential energy of the system can only take on values given by this formula. The energy of the nth state that's allowed, the nth allowed state, is minus 13.6 electron volts divided by n squared, where n is one of the natural numbers. It starts at 1, and then 2, and then 3, and then so on. And if you make an energy plot of the allowed energies, and you can see here also sketched in is the potential energy, you can see that the allowed values start at negative 13.6 electron volts, that's E1, and then E2 goes all the way up to negative 3.4, and then E3 goes to negative 1.51, and then the spacing between the energy levels gets quite small as n becomes large, approaching 0 as n approaches infinity. But so the low energy levels, 1, 2, 3, and so on, have a large spacing, and the high energy levels, 4, 5, 6, 7, 8, and so on, the spacing gets smaller and smaller and smaller as n gets larger. So the idea is the electron can be in state 2, or it can be in state 3, or it can be in state 4, or state 1, but it can't be between those two states. There's no allowed energy between negative 13.6 electron volts and negative 3.4 electron volts. There just isn't any place, any way the electron can be that nature seems to be happy with. So that's kind of one way to think about it, at least. Now, electromagnetic energy, one form of which is visible light, turns out to be chunky all the time. You can only get discrete amounts of electromagnetic energy, which we call photons, or sort of chunks of light. Now, the energy of different types of electromagnetic wave vary quite a lot. The energy of a single photon of different types of electromagnetic wave varies quite a lot. So a radio wavelength photon has an energy of a millionth of an electron volt. Visible photons have energies of a few electron volts, and X-rays have energies of 10,000 electron volts each. One X-ray photon has 10,000 times the energy of a visible photon that your eye is sensitive to. And gamma rays have energies that go from 1,000,000 electron volts on up. So there's a tremendous range of energies associated with different wavelengths of electromagnetic radiation, and this table just sort of gives you a sense of how those go. In the visible spectrum, the energies go between 1.8 electron volts and 3.1 electron volts. So you can see that that's an extremely narrow range of energies given the full electromagnetic spectrum, which goes from basically 0 to infinity. Now here's the thing. All waves, whether they're electromagnetic waves or water waves or waves of people waving their hand at a stadium in a wavy way, obey a relationship between the wavelength of the wave, the frequency of the wave, and the speed of the wave. And to motivate that relationship, I got a little demo here I want to show. Okay, so this is a movie of a moving wave. Let me play the movie for you so you can see what it looks like. The wave just moves to the right. It's got a relative amplitude of 1, which just means that when the wave is at 1 at the top of the plot, it's at maximum height or maximum value, whatever the value. For an electric wave, it would be an electric field, or a magnetic wave, it would be a magnetic field, or for a water wave, it would be the height of the water, that kind of thing. For a sound wave, it might be the pressure. And the point is, as time goes on, the peak moves to the right, and the trough moves to the right, and everything basically moves to the right over time. The time it takes, if you look at a single point on the wave, say look at this point right here, and watch as time goes on. That point goes down, and then that point comes back up again. So if you watch a point on the wave, it oscillates up and down. At any given value of x, the value of the wave oscillates up and down in time at that value of x. It's sort of like if you have a water wave and you stick a cork on the water. The cork doesn't move when the wave goes by, it just oscillates up and down. And the period of that oscillation is called the period of the wave. That's the period of the wave. The time it takes a point at a fixed location to go through one complete oscillation at that point. Now the distance between successive maxima in the wave, say the distance between this point and this point, is called the wavelength, and that's also the distance between this point and this point, and it's the distance between any part of the wave and the next time that part of the wave happens in space. So that would be from where it's going up and passes through the origin here to where it's going up and passes through the origin here. That's a wavelength, the distance between those 2 points. Now what's interesting is to try to see if you can determine the speed of the wave. And what I'd like you to do is to focus on a peak, say this peak, and watch it move to the right and look how far does it go in the time it takes the next peak to arrive at the same place. In other words, notice that if I put my mouse at the location of the peak now, and then I wait, how long does it take for the next peak to come? It's a period. But then if you look, how far does the next peak move? How far does this peak move in the time it takes for the next peak to appear? You'll notice it's a wavelength. So the wave travels a wavelength in the time it takes for a single point on the wave to oscillate one full time. In other words, the speed of the wave, the distance divided by the time, is the wavelength divided by the period. Now, 1 divided by the period is called the frequency of the wave, so that means since it's the wavelength divided by the period, it's also the wavelength times the frequency. And that motivates the formula C equals lambda times F. For electromagnetic waves, in addition to that, it turns out the energy of the wave is directly proportional to the frequency. And since the frequency is the speed divided by the wavelength, you can write that as speed divided by wavelength times a constant, or just frequency times a constant. The constant of proportionality is called Planck's constant. It's indicated by the letter H, and it has a value of 6.63 times 10 to the negative 34 joule seconds, an extremely tiny number. It is the tininess of this number which caused the chunkiness of energy and matter to go undetected until the early part of the 20th century, by and large, or the late part of the 19th century. And we're going to find out later that it's the smallness of this number that allows us to ignore quantization in our sort of daily lives. So how does quantization manifest itself in the laboratory? Often it does so through the process of emission and absorption of electromagnetic radiation. So when an electron jumps from one level to another, it either emits a photon or absorbs it. So when it goes from a high level to a low level, it'll often emit a photon with energy equal to the difference in energy between the two states that it's jumping between. And if you've got electromagnetic radiation in a cavity or in a region where there are atoms such that the energy difference between two neighboring states of the electrons in the atoms corresponds to a photon energy that's present in the electromagnetic radiation, then the electrons can absorb a photon and jump from a lower state to a higher state. That's the idea. Now they can only absorb a photon if they're in the state that has a higher state where the energy difference is equal to the energy of a photon in the radiation. But we'll see how that works in the examples in class, but that's the idea. So in order to absorb a photon, you've got to have an energy difference between two neighboring states that's equal to the photon energy. And when you emit a photon whose energy is equal to the energy difference between two neighboring states. So let's talk about temperature. If you have a bunch of atoms or a bunch of things in a system that can take on different energies, the probability of having a particular energy depends on the temperature. So you can see the way this formula works, e to the minus energy divided by kT. If the temperature is very high, the probability of having a high energy goes up. But if the temperature is very low, the probability of having a high energy goes way down. It goes exponentially down. So, and this constant out in front, this P0, is just a so-called normalization factor. You can see that it's equal to the probability when the energy is 0, but basically we just adjust P0 so that the probability of having any energy, if you enumerate all the different energies and calculate the probability of all the different energies, they're all proportional to P0. So you can scale P0 so that the total probability of having any energy at all turns out to be 1. Now let's consider a gas at low temperature. If you have a bunch of atoms in a gas at low temperature, basically the probability of being in even the first excited state, above the ground state, is extremely tiny because the temperature is so low and the energy difference between those two states is so large that the probability of being in n equals 1, say, if this were a hydrogen atom, you'd say the probability of being n equals 1 is vanishingly small, and so all the atoms in the ensemble of atoms are going to be in the ground state. On the other hand, if the temperature is high, then the probability of being in n equals 1 or n equals 2 or n equals 3, it diminishes with energy. There is still an exponential decay, but it doesn't diminish so quickly that the probability of being in these upper states is completely negligible. And so you assume that if the gas is at a very high temperature, that there's some finite non-zero probability of being in these upper excited states. And what that means is electrons in those states can participate in transitions that require them to start in n equals 1 or n equals 2 or n equals 3. But if it's at a low temperature, then the only transitions that are available are transitions where the electrons start in n equals 1. So they can go from n equals 1 to n equals 2, and n equals 1 to n equals 3, but they can't go from n equals 1 to anything, or n equals 2 to anything, because there's no electrons in any of those states, because the temperature is too low. And that's an important consideration. You'll see how that works when you do the homework problems, and we've also talked about that in a couple of the warm-ups, but that's the idea. Electrons can also be excited by colliding with other particles in the gas. So if you have a bunch of high energy free electrons that you bombard a gas with, they can collide with atoms that contain electrons in lower states, and in that case the energy exchange between the free electron and the atom is not quantized. I mean, it's quantized in the sense that the electron in the atom can only jump between allowed energy states, but the free electron can take on essentially any energy. So that means that as long as there is sufficient energy for the transition to occur, the free electron doesn't have to have any particular amount of energy in order to contribute to that transition. Let's put it that way. If the colliding electron, the free electron, has enough energy to raise the energy of the bound electron above 0, then the bound electron will essentially become free. And so that process is called the ionization of the atom. The previously bound electron can actually be removed from the atom and allowed to wander around. The atom then becomes an ion, and that process is called ionization. So let's talk about vibration. Vibration is another kind of bound process. You have say for example an atom bound to a larger molecule, and it can wiggle there, so it's kind of like a mass on a spring, but it's stuck, it can't get away, and the fact that it can't get away means that its energy levels are going to be quantized. And so the vibration has a natural frequency, which is just the square root of the spring constant divided by the mass. It's exactly like a classical oscillator. But the allowed energies are not just like the classical system. The allowed energies are limited in the sense that the difference between neighboring allowed energies turns out to be h bar times the natural frequency. Now h bar is a constant related to h. H is Planck's constant, the 6.63 times 10 to the negative 34 joule seconds. H bar is simply Planck's constant divided by 2 pi. Remember that omega is the natural frequency times 2 pi. H is the Planck's constant divided by 2 pi. So h times omega naught is nothing other than the old Planck's constant times the natural linear frequency. Omega is the angular frequency. H bar has a 2 pi in the denominator to compensate for the 2 pi in the numerator of the angular frequency. So that's where all the 2 pi's have gotten to. But a lot of times we don't want to mess with all the 2 pi's, and so we use H bar in order to prevent us from having to use up a lot of chalk, writing 2 pi's all the time. Okay, enough of that. So what that means is if you have a potential energy that's a quadratic, as in the simple harmonic oscillator, the energy levels will be equally spaced, and the difference between neighboring energy levels will be h bar times the natural frequency of the oscillator. And it turns out there is a smallest energy state, which we call E sub 0. That's the n equals 0 energy. And the book doesn't say it, but I don't see any reason not to say it, so I'm going to go ahead and tell you that for a simple harmonic oscillator turns out to be a half of h bar omega 0. And for a simple one-dimensional harmonic oscillator. You can think of a higher dimensional harmonic oscillator as a collection of one-dimensional harmonic oscillators, and we'll talk about that later in chapter 12 when we get to that material. But that's the idea. So the main point is there is a lowest energy level, E0, and the difference between neighboring energy levels is always the same, h bar omega naught. That's for a classical simple harmonic oscillator. Now, you can think of a diatomic molecule as approximately a simple harmonic oscillator, at least at low energy. You can see that the potential isn't really quadratic. This is the so-called Morse potential, and the Morse potential looks roughly quadratic at low energy, but as the energy goes up, the potential rises more slowly in the direction of greater separation and rises more steeply than quadratic in the direction of diminished separation. And so while the simple harmonic oscillator approximation works well for the lowest energy states, as the energy level goes up, the spacing between the energy levels doesn't remain constant forever as it would in a purely quadratic potential, but the spacing actually gets closer together as you go up in energy, sort of reminiscent of the hydrogen atom, but the math is quite different, but the qualitative behavior is not that different. So a real diatomic molecule sort of behaves like this. The other thing a diatomic molecule can do is to rotate, and so it can spin around, and it turns out that that rotation, it's a bound kind of motion, and so it's also quantized. Anytime you have a bound system in motion, it turns out it's going to be quantized. The quantization is interesting in the sense that the separation between neighboring energy levels as the spin gets larger and larger actually goes up. But the energy differences are very small in most realistic systems, and so if you look at the spectrum of a diatomic molecule overall, you've got the electronic levels of the electrons in the sort of the valence electrons in the molecule that can change energy states, and for each electronic level there are multiple vibrational levels. So for example, at that top electronic level there are 4 vibration levels that are shown. The middle one has 4 vibration levels, and the bottom one has 4 vibration levels shown. But each vibration level, each quantized energy of vibration, also has associated with it a family of rotation energy levels that are quantized. And so the full spectrum of a diatomic molecule has many, many, many energy levels associated with rotation, vibration, and the electronic excitation, the different electronic energy states, like those of the hydrogen atom. So it can get quite complicated, but we're going to try to keep it simple and not make it too complicated, but that's kind of how it all fits together. I just want to say a few words about the fact that nuclei, we've been sort of ignoring the nuclei and talking a lot about electrons, but the protons and neutrons in a nucleus also have levels, sort of like the levels of electrons orbiting in atoms, and protons and neutrons can jump from one level to another, and they can emit and absorb photons in a similar fashion. The difference, of course, is that the energy differences between levels in the electronic structure are electron volts. The difference in energy levels for a nuclear situation are more like millions of electron volts, so that the appropriate radiation to talk about when discussing nuclear transitions is gamma radiation. And the other point is that neutrons and protons are actually composed of quarks, and quarks can have different states, just like electrons can in atoms. And so protons and neutrons can actually, given enough energy, you can convert them into you can give them other energy states, and the energy differences in those cases are so large that people didn't recognize them as protons and neutrons anymore, and they actually gave them other names, but it turned out to be protons and neutrons with other energy levels. And there's a whole world of particle physics associated with the different flavors of quarks and the different colors of quarks and how they work. But the basic idea that you have quantized energy levels and you can make transitions from different energy states is still sound, even in that rather more exotic context. So that's basically it. We'll see you guys next time.
Hey guys, welcome back. Chapter 9 is called Multiparticle Systems in the textbook. In looking over it, I decided that really what this chapter is about is getting more realistic about real systems. So I call it getting more real. Basically, real systems have lots of little pieces, and they all you have to take into account all the parts of the system together to figure out what's going on. And so it's complicated. I have drawn here, or have diagrams here of a couple of example systems from the text. In one case, we've got multiple objects that are sort of spinning and whizzing around. In another case, we've got a couple of blocks connected by a spring. But obviously, this thing is somewhat complicated in that we've got 3 different parts of the system, all that can move relative to one another, and stuff can happen. Work can be done. And we need as a way to sort of catalog what's going on and get our heads screwed on and try to think about it systematically so that we don't get lost in a bewildering morass of complexity. So let's see if we can do that. First of all, I want to point out that objects can change shape, and we've never dealt with that so far in this course. The fact that an object can change shape during the course of some process, and we need to be able to figure out how to deal with that. Internal forces can do work, and they can change their internal potential energy in that way. And also, forces are often very difficult to work out in detail, but oftentimes we're going to discover that energy is an easier concept to work with in these complicated systems. And so when it's possible to do so, it's useful to consider the energy rather than the momentum principle when dealing with these complicated systems. So what are we going to do? The first thing we're going to do is to divide motion into 2 categories, and to notice that even in a complicated system, there's sort of an average position of all the stuff in the system, and that average position we're going to call the center of mass. It's kind of a vague definition at this moment, but we'll make it more formal here momentarily. And then the other is that there is also relative motion of the parts of the system about the center of mass. The motion of the center of mass we're going to call translation, and it will have an associated kinetic energy called translational kinetic energy. And the relative motion of the parts of the system about the center of mass, that's going to also have some kinetic energy associated with it, and we're going to call that relative kinetic energy. So let's march ahead. We want to define center of mass more carefully. I do literally mean it's the average position. If we were to divide any object, no matter how complicated, into equal mass pieces, and then compute the average position of all the pieces, that would be the center of mass. So let's take a look at that. If you think about that definition for a little bit, you'll realize that it's equivalent to this formula. And we're going to work on this in class, and I'll actually take you through a process where we have an object, divide it into equal mass pieces, and then recognize that if there are two pieces that are almost at the same place, we can sort of bundle those together and weigh their position twice. But then that's equivalent to weighing the each position in the object by its corresponding mass. And then if you just calculate the straight algebraic or straight arithmetic mean of the positions of all those pieces, you will discover that it's the same as this formula. So anyway, this is the expression we're going to use to compute the position of the center of mass. If you multiply both sides of this expression by the total mass and then take the time derivative, on the left you get the total mass times the time derivative of the position of the center of mass, and that's equal to the individual masses times the time derivative of each mass's corresponding position. But I want you to look at that for a second. Mass 1 times its velocity plus mass 2 times its velocity plus blah 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 blah, that's nothing other than the total momentum of the system, the sum of the momenta of all the pieces. But on the left what I have is the total mass of the system times the rate of change of the center of mass. That's the velocity of the center of mass. So from a momentum point of view, I can replace all the little momenta of all the pieces with simply the total mass times the velocity of the center of mass. And that's essentially what we've been doing all along, is we've been looking at a block that flies through the air. All we've been paying attention to is the center of mass, and we've been calculating its momentum as the velocity of the center of mass times the mass of the whole block. And we've been completely ignoring any rotation or wiggling or anything else that's been going on, and it's worked out okay. So you can see that the total momentum is the sum of the momenta. That's the mass times the velocity of the center of mass. And that also is going to allow us to compute the translational kinetic energy, because we just can calculate 1/2 mv squared, and it's the total mass times the velocity of the center of mass squared. That's if you could think of this as a definition, if you like. This is what we mean by the translational part of the kinetic energy. Now let's do an example. Let's suppose we have a 3 kilogram mass at the location 0, -1 meters, a 1 kilogram mass at 1, 2, and a 2 kilogram mass at 2, 1, and I want to compute the position of the center of mass. So what I do is to simply use the formula 1 kilogram times the position of the 1 kilogram mass plus 2 kilograms times the position of the 2 kilogram mass, 3 kilograms times the position of the 3 kilogram mass divided by the total mass. And before I continue, I ought to point out that if you divide the 2 kilogram mass into 2 1 kilogram masses and the 3 kilogram mass into 3 1 kilogram masses, then you can see that in fact what we're computing here is nothing other than the average position, the straight arithmetic mean of the position of all the 1 kilogram masses that make up this system. Notice that the 2, 1, 0 gets counted twice because there are 2 1 kilogram masses there, and the 0, -1, 0 position gets counted 3 times. That's because there are 3 1 kilogram masses there, and you divide by 6 because there are 6 1 kilogram masses altogether. So it's simply the sum divided by the total number of 1 kilogram masses, and it works out. So if you do the calculation, you can see how it turns out. You end up with 0.83, 0.1670. I'll go ahead and draw that on the picture. You can see that that looks like sort of the middle of the picture. That's the average position of all the mass in the system. It's a little bit closer to the 3 kilogram mass than it is to the other guys, and that's just because there's more mass down there. Also, I want to point out that the position of the center of mass in this example is at a location in space where there is actually no mass. So there's no rule that says the center of mass has to be at a place where there's any mass. It's simply the average position of all the mass that there is. Okay, let's talk about energy and momentum. You can work out the momentum principle for the combined system. The result is easily remembered. It's just that the rate of change in momentum of the entire system is equal to the net force on the entire system due to the surroundings. So all the internal forces cancel out because of the reciprocity principle, and the rate of change of the total momentum is simply equal to the net force. Now remember, the total momentum is related to the velocity of the center of mass. So that means that if there's a net force acting on the system, that the velocity of the center of mass is going to change. That's the idea. You can also calculate the gravitational potential energy near the surface of the Earth of all the masses, and it turns out because the center of mass is at the average position of all the mass, that it also has the average height of all the mass, and because gravitational potential energy near the surface of the Earth is just proportional to height, the average potential energy turns out to be equal to the average height times mg. So that's easy enough to do. And finally, the kinetic energy we can separate into the piece that we already identified has having to do with the motion of the center of mass. That's the translational kinetic energy. But there can also be rotational kinetic energy, which has to do with velocities that are perpendicular to a line going from the center of mass to the particle, and vibrational energies which are parallel to the line going from the center of mass to the particle. And basically the vibrational part is the radial motion, and the rotational part is orbital motion, more or less. Okay, what do we mean by a point particle system? A point particle system is sort of what you get when you look at the system from a great distance away. And you're so far away you can't see any of the internal degrees of freedom, and none of the internal motions are visible. You know they're still there, but they're not really visible because the thing is so far away. Let's see what that might look like. So I have a system, I look at it from such a great distance that I don't see all the internal structure. All I see is that I've got a net force acting on the system. And if the thing changes its position, that net force acts on the system as it changes its position of its center of mass and does work. So the idea is, if I sort of smudge out all the internal motions and all I see is the average position of all the stuff, then it looks just like a point particle, and I can treat it like a point particle. I get that the change in the translational kinetic energy is equal to the net force times the displacement of the center of mass. So the idea is, if I don't see any of the internal motions, the only energy there is translational kinetic energy. And so I can compute the change in the translational kinetic energy without worrying about the details of any of the relative motions of the particles relative to one another, or any of their changes in internal potential energy. It's simply the net force dotted into the displacement of the center of mass. And of course I can, if the net force happens to be a variable, it's not constant, then I can convert that into an integral. But I would say this is the trickiest part from the whole chapter to become familiar with. After you get the translational part of the change in kinetic energy, you know that if there is any other change in kinetic energy, it's got to be the relative part, the rotational and the vibrational part. So that means that you can use the full system energy principle to compute the rotational and vibrational changes in kinetic energy. So that's the idea. We start with the point particle system, work out the translational change in the translational kinetic energy, and then use the full system energy principle to work out the other ones. And that's the way that works. So let's talk about rotational kinetic energy. We need to develop an idea of rotational inertia. We need to recognize that during rotation, mass that's far from the axis moves a lot more than mass that's nearby the axis. And the axis doesn't have to be the center of mass in all cases, but it's often useful. If a particle is just freely moving through space, it turns out the axis would be the center of mass. So generally that's the way we're going to deal with it. And rotational kinetic energy also depends on angular velocity. So the faster something's spinning, the more rotational kinetic energy you expect. So, And of course, we already know that translational kinetic energy depends on the center of mass velocity. So consider here a simple object with 4 masses connected to rods. The thing is spinning around in some way, and the masses are moving. But it's a rigid object, so what that means is everything has to be moving with the same angular velocity. So omega is 2 pi over the time it takes for the thing to go around once. And we know that kinetic energy, if we assume that let's say its center of mass is stationary, it's just sitting here spinning, then the kinetic energy is the sum of the kinetic energies of the pieces, but it's all rotational kinetic energy, because there's no component of velocity going in and out, and there's no velocity of the center of mass, so the only kinetic energy that remains is the rotational flavor. And I want to point out that the velocity of any one of these masses is just the circumference of the circle, 2 pi r, divided by the time it takes to go around once. But of course we already know that that's nothing other than omega times r, and so we can put that back into the expression for kinetic energy. But notice every single mass has the same omega, so the omegas actually factor out. And what you get is 1/2 of the sum of the mr squareds times omega squared. Notice the similarity of that expression, the sum of the mr squareds, to the center of mass calculation, the sum of the mr's, divided by the sum of the m's. There's a similar thing going on there. The difference is that the r's here are all squared, and so you can never get a negative rotational inertia. This I thing is called the rotational inertia. You can never get a negative value for that. Whereas you could obviously have a negative value for the component of the center of mass. So there's slightly different expressions, but that's how it turns out. The rotational kinetic energy is nothing other than 1/2 times the rotational inertia times omega squared. Notice the similarity with the translational kinetic energy, which is 1/2 times the total mass times the translational velocity of the center of mass squared. Here we have the rotational angular velocity of the system about the center of mass squared. Okay, let's formalize that a little bit. That means that the rotational inertia is the sum of the m times the r squareds, and if I have a continuous distribution of mass, I can turn that into an integral and make that the sum of r squared times dm, where dm is the small chunk of mass. For example, let's try a hollow cylinder. If we have a hollow cylinder, that means all the mass is at a single radius, capital R, and that means r is a constant, because anywhere there's mass, r is always the same. So I can take the r outside of the integral, and then I just get r squared times the integral of dm, which of course is just the sum of the masses of the system, and that's just mr squared. So a hollow cylinder is quite easy. It's just mr squared. Let's go ahead and do a solid cylinder. That's a little bit more complicated. A solid cylinder has mass from r equals 0 all the way out to r equals capital R. And I want to evaluate this rotational inertia integral using the solid cylinder. So let's look at that. First of all, it has a radius capital R, has a thickness little t. Let's say it has a density rho. And what I want to do is to compute this integral. I need to isolate a little chunk of mass that has the same r everywhere from the origin. I know that's a hollow cylinder, so I know that its rotational inertia is dm times r squared. And I need to add those up for all the hollow cylinders that make up the solid cylinder. So a particular chunk, a particular piece of mass has a radius r, a thickness dr, and let's think about what's the total mass of the entire solid cylinder. Well, it's the area of the side of the solid cylinder times the thickness, that's the volume of the solid cylinder, times the density. So the total mass is rho pi r squared t, and the mass of that little piece that I've isolated there is the area the yellow part of the area of the piece times the thickness times rho. So it's the volume of the little piece times rho. But what is the area of that that surface, the yellow-colored surface of the hollow cylinder? Well, it's nothing other than the circumference of the circle times the dr, the width of that yellow strip. And if I put that back into the dm, I get the density times the thickness times 2 pi r times dr. And now I can put that back into the original integral, and I can compute the integral. Notice that rho, t, and 2 pi are all constant, so they come out, and I end up with the integral of little r cubed dr from the origin all the way out to big R. Of course, that's an easy integral to do. It's just big R to the 4th over 4. I can simplify, and I get that it's pi rho t r to the 4th over 2. Now, the thing is, I don't necessarily want to have to find the density and the thickness of every cylinder, but remember, I already know the total mass of the cylinder is rho times pi times capital R squared times t. And notice I've got a rho times pi times capital R to the 4th times t. So I could factor out the mass of the cylinder, and it turns out then I get the simple expression 1/2 times the mass of the entire cylinder times r squared. So remember what we got for the hollow cylinder, it was just mr squared. For a solid cylinder, it's 1/2 mr squared. And you can, of course, reproduce this calculation for a variety of different shapes. It's great fun. If you're bored sometime, you can go and calculate the rotational inertia of all these different shapes. But I've gone ahead and made a little tabular representation here for you in case you're curious. I think there's also a table like this probably in the book somewhere. If not, you can Google it at any time. These are well-known results that people have worked out a long time ago. Anyway, let's take a quick review of some of the variables we've been dealing with, because I think this is a good time in the course to stop for a second and sort of reflect on all the different variables we've dealt with. First of all, there's the kinematic variables of position, velocity, and acceleration that are related to each other by time derivatives. The velocity is the time derivative of the position, the acceleration is the time derivative of the velocity. We have this concept called mass, which has to do with how much stuff there is. And we have this idea of momentum. Of course, this is the non-relativistic momentum, only for speeds much less than the speed of light. But we could generalize that. We've got the idea of force, which has to do with the rate of change of the momentum of a system. And we've got the idea of kinetic energy. In this case, it's the translational part of the kinetic energy. It's 1/2 the mass of the system times the velocity of the center of mass squared. But I just put 1/2 mv squared to sort of remind us of the structure of the thing. What I want to point out is we've added a rotational form of kinetic energy, but we're going to be dealing with problems that involve all kinds of rotation, and I just wanted to take a minute to discuss the relationship here. When we're describing a rotation, we need something like position for rotation, and the position turns out to be the angle. So if you rotate a thing a certain amount, that is represented as an angle. But then the angle can change in time, so we have an angular velocity, the rate of change of the angle. And the angular velocity can change in time, so we have an angular acceleration. And you may remember that there were some algebraic solutions to the momentum principle, basically, that were correct as long as the force was constant. We're going to find out, and as long as the acceleration was constant, and we're going to find out that there are similar equations for the case when angular acceleration is constant. So we'll take a look at that in class. Now, for mass, there is a sort of analogous quantity. It's called the rotational inertia. So rotational inertia plays the same role that mass plays in translational motion, but it does it in rotational motion. And we're going to find out soon that there is an angular momentum associated with rotation. Now there are two flavors of angular momentum. There's orbital and spin, and this turns out to be the spin flavor. There's also another type. This I omega is the spin angular momentum. We're going to find out that there's another one that's related to the angular momentum an object has when its center of mass orbits another object, or orbits the origin. Their idea of force has an analog. It's called torque. Notice that the force turned out to be the rate of change in the momentum. The torque is the rate of change of the angular momentum. And I like to bring up a cause and effect nature here. The net force causes a rate of change in momentum. The net torque causes a rate of change of angular momentum. Torques are brought about by forces, but you have to calculate a torque. So we'll see how to do that soon enough. And finally, there's the rotational kinetic energy, 1/2 I omega squared. What I want to point out here is that without even knowing what all these goofy letters mean, we can already see a pattern in the relationships between them. So if you know a relationship that exists between the translational quantities, position, velocity, acceleration, momentum, force, kinetic energy, you already know the relationship that exists between the rotational quantities, because it's simply a question of substituting the right letters and putting them into the relationship. So I only want to bring up this table now because it's good to recognize as early as possible that there are these analogies that exist between translational motion and rotational motion, and you can take advantage of your knowledge of the translational motion in order to get insight into the rotational motion. Okay. So we're going to do some examples. At this point, I'm only going to work out one example, but I'm going to give you an example to work out and bring to class on Friday. And in order to do it, I want you to go find the Rolling Motion podcast. I put a URL on ACE so you can track it down. For those of you watching on YouTube, you can go to the playlist and find the Rolling Motion podcast and look at that. What we're going to do right now is an example of a person crouching and jumping, and that's an example of a body changing shape. The strategy is to work out the point particle system first, and once we know the change in the translational kinetic energy, we can use the real system to find out the change in the internal energy of the system. So that's the idea. We have a 1.73 meter tall vertical jumper. He crouches down, leaves the ground with a speed v0, assuming they can lower their center of mass by 25% of their height, and that they can exert a normal force 3 times their weight. In other words, they can push down on the ground with a force 3 times their weight. What speed can they achieve? How high is the center of mass after the jump? Is their center of mass after the jump? Let's look at that. So we're going to work out the point particle system first. They're going to crouch down, and then they're going to jump. So I have two images here. One is before they start moving as they're crouched down, and the second image is just as they're about to leave the floor. So they're completely uncrouched, and they're moving with some speed upward. They're moving with some velocity upward, but the speed is v0. So we can use the point particle system result that the change in the translational kinetic energy is equal to the net force on the point particle system times the displacement of the center of mass. Now, the point particle system, by definition, is a system consisting only of a point particle, which has the mass of the entire system. So we're going to scrunch this person into a point that's located at their center of mass. And we're going to notice that the net force acting on them is the normal force plus the weight, and it gets displaced by a distance a quarter of their height, right? Because their center of mass is going from the point it was when they were crouched down, a quarter of their height below their original center of mass location, and it's going to go back up to the original center of mass location at the moment they leave the ground. And we can work that out. Now, the change in the translational kinetic energy, of course, they start at rest. So the change in the translational kinetic energy is 1/2 mv0 squared. The weight acts down, the normal force acts up. And so the net force acting on them is going to be, actually the normal force was 3 times their weight. So the net force is going to be 2 times their weight times their displacement. If you put in h for their original height and calculate all this, you end up with a speed that's about 4.12 meters per second, given their initial height. So that's the kind of thing you can get with the point particle system. Next, we can analyze the real system. So we forget about the point particle system, but we remember that we worked out the speed and we worked out the work done, and so on. The change in the energy of the system, the real system now, is equal to the work done on the system by the surroundings. Now we have to decide what our real system is going to include. I've chosen to include the jumper, include the Earth, but not anything else. So let's see how that works. Because we've got the jumper included, we've got his change in translational kinetic energy. We've also got the Earth included, so we get a change in the interaction potential energy between the jumper and the Earth. And I'm going to say that there's a change in the internal energy of the jumper, but there's no work done on the jumper by the surroundings, because the contact point between the Earth and his feet does not move, so the Earth actually isn't doing any work on the jumper. So those guys have to add up to 0. Now, if you put in the known change in height of the jumper as it goes from A to B, and you put in the known change in translational kinetic energy, we can actually calculate the change in internal energy. The change in internal energy turns out to be minus 3/4 of mgh. And that means that's the energy. So if there were he ate some Wheaties this morning and that jump required some energy on his part, this would be the amount of energy that was extracted from his body chemistry or physiology or whatever. His muscles is the idea. Okay. Now, what about how high he jumps? How do I handle the jump? So the idea here is we create a new point, we'll call it point C. Right now we've been dealing with the point when he's crouched and the point when he just got off the floor. Now we're going to create a new point called C when he reaches his maximum height. And at that moment his velocity goes to 0 and he reaches a delta y that we want to find out. We want to know what is the delta y, how high does he go. So let's work it out. Again, the change in the energy is the work done on the system by the surroundings, but we know the floor does no work, and we're including the Earth in the system, so we don't include that in the surroundings. We know the translational kinetic energy is 0 at the top and 0 at the bottom, so there's no change in translational kinetic energy. So the basic idea is the change in the gravitational potential energy must be equal to the change in the internal energy. But we already worked out the change in the internal energy. That happened between points A and B, and so we can simply put that in, and we know that that is the only energy available to raise the potential energy. So we can solve then for delta YAC, and we find out that it's 3/4 of the height. And that's pretty much the end of the story. That's how it works. So I hope that was helpful, guys, and we'll see you next time. Hi, guys. This is going to be a very quick set of slides on the overview, basically an overview of the ideas of Chapter 10. I'm going to try to cook up some additional slides, which will be sort of homework-style problems kind of worked out. If I have time, I will do that. So here we go. Let's talk about Chapter 10. It's all about collisions, stuff crashing into other stuff. And the main thing is we're going to make an approximation in this chapter that's actually very good under most circumstances, and that is that when objects collide, they interact with short-range forces that are only active for a very short period of time during the collision. That has some consequences. Among them are that the total momentum of both objects taken together is unchanged during the collision. It also means that while the translational kinetic energy may or may not be unchanged, the total energy is unchanged. And if you look at the collision from the center of mass point of view, it turns out in many situations it simplifies the analysis. So those are the main points. By the way, those situations in which the translational kinetic energy is unchanged are a special class of collisions, which we call elastic. Those in which the translational kinetic energy is not unchanged are called inelastic. And we'll see how that works here in a little bit. One of the consequences of this is that you can neglect external forces, forces that act on the system due to the interaction with the surroundings can be neglected during a collision because the time period is so short. The forces that are large are the action and reaction forces between components of the system. So I'm thinking of the system as all the objects that are colliding. Under normal circumstances, that's two objects that collide with one another. The forces between the two objects are much, much larger than any forces from the surroundings acting on either of the objects. And so we can basically neglect the surrounding forces and only worry about the action-reaction pairs. But you know, the momentum principle says that the change in the momentum of the system is equal to the net force acting on the system times the change in time. Well, the change in time is very small, and the net force is only due to the surroundings. Because if you think about it, the reciprocity forces internal to the system have a special property. So one idea is, well, why don't the action and reaction forces contribute to the net force? You ought to know that off the top of your head, but I want you to think about it. If you can't figure it out, then ask me. But I'm hoping that you're saying, well, of course they don't contribute because blah, right? Okay, very good. Okay, so let's do an example that illustrates the magnitude of these forces. Basically, this is just a ball dropping, hitting the floor and bouncing up. It's a 100-gram ball. It strikes the floor at a speed of 6 meters per second with a momentum pointing down. It rebounds with a speed of 5 meters per second with momentum pointing up. And all I want to do is figure out what's its rate of change of momentum, or what's the change in momentum per unit time. Notice that the collision with the floor only takes 1 millisecond, so it's very tiny. What's the change in momentum? Well, it's the mass times the change in the y component of velocity. Only the y component of momentum changes, so I can only have to worry about the y component of velocity. Turns out it's plus 5 minus negative 6 times 0.1 kilograms. It works out to be 1.1 kilogram meters per second. Doesn't sound too dramatic, but then when you figure out what is the rate of change in momentum, how much does the momentum change per unit time, you get a factor of 1,000 because of the 1 millisecond interaction time. And so the force of the floor pushing up on the ball is something on the order of 1,100 newtons. Now the weight of the ball, the force of the Earth acting on the ball, is only 1 newton. So compared to the force of the collision between the floor and the ball, the weight is relatively negligible. And that's especially for a short period of time. Of course, the weight continues to act over a long period of time. The force of the floor only acts for a millisecond. So if you only take into account that brief period of time between before the collision and after the collision, the force of the floor, or the force of the Earth pulling down, in other words, the weight of the ball, is completely negligible. That's the idea. Now, if you think of the system as the two objects that are colliding with each other as the total system, the momentum of the entire system is unchanged. That just means that the net force times delta t is going to be negligibly small, because the internal forces don't contribute to the net force, and the external forces times this little change in time don't significantly change the total momentum. That's the idea. Why is that useful? It's useful because if you add up the momentum of all the objects before the collision, you get the same thing as you get when you add up the momentum of all the objects in the collision after. Again, usually all the objects is 2, because normally only 2 objects are involved in a collision. Although there's no, in principle, there's no restriction. Often we'll find that it's 2 objects. And this also works both in one-dimensional collisions and 2- and 3-dimensional collisions. The other thing is, what about the energy principle? The energy principle says the change in the energy of the system is the work done on the system by the surroundings, plus the heat transferred into the system due to a temperature difference. But because the collision is very brief, there's no time for stuff to move around, and therefore there's no time to do any work. It takes time to transfer thermal energy, and if a collision is very brief, there's no time for that to happen. So the idea is that in a collision, if you just look at the moment before the collision and the moment after the collision, it is extremely good approximation to say that the total energy of the system, both translational and internal, is unchanged during the collision. So that means the energy before, the total energy before, and the total energy after are equal. That's the idea. If it turns out the translational kinetic energy is the same before and after, then we call that collision elastic. So collisions that produce no change in the internal energy, in other words, in which the translational kinetic energy is unchanged, are called elastic. Inelastic collisions do produce changes in internal energy, and totally inelastic collisions produce the maximum possible change in internal energy. And those are collisions in which the two objects colliding with one another actually end up sticking together. That's a totally inelastic collision. And let's look at an example. Let's say we have an object moving to the right with the speed v1, and the second object, m2, is initially at rest. If they are involved in an inelastic collision, it means the two objects actually stick together. Because they stick together, it means their final velocities have to be equal. And all we have to do then is write down the fact that the momentum before and the momentum after have to be equal. If I put in an expression for the momentum before, which is just m1 v1 initial, and set that equal to the momentum after, which is m1 plus m2 times v final, I get that v final is m1 divided by the sum of the masses times the initial velocity of mass 1. That's simply demanding that the total momentum of the two-block system is the same before and after the collision. Easily enough. Let's look at an elastic collision. This one I'm going to assume is perfectly elastic, and that means that the translational kinetic energy is unchanged by the collision. Again, we have a mass m1 colliding with a mass m2 with an initial speed v1 initial. In order to be in a totally or completely perfectly elastic collision, it turns out both the masses have to have a speed afterwards. They cannot stick together. And so we have v1 final and v2 final, two different velocities after the collision. We simply put in the fact that the momentum has to be the same before and after, and that the translational kinetic energies have to be the same before and after. And then we've got two equations, and we've got two unknowns, the final velocity of mass 1 and the final velocity of mass 2. If you plug all that in, you get two results. You get the final velocity of mass 1 is the difference of the masses divided by the sum times the initial velocity of mass 1, and you get the final velocity of mass 2 is twice the initial velocity of mass 1 divided by the total mass of the system. And we can work that out in class. You can do it as a homework problem, but it's not too bad. It's not too bad. All right. And finally, what happens if you go to 2 dimensions? Both of those examples were in 1 dimension. In 2 dimensions, let's say I have a mass m1 colliding with a mass m2, and they interact. The distance between the velocity vector and the center of mass 2 is sometimes called the impact parameter. Okay, that's just some terminology. And if they collide with one another, what happens? They kind of move along, and I've got some dotted lines here that are supposed to represent their trajectories, not the detailed trajectory during the collision, but they are sort of the asymptotic directions of motion before and after the collision. The angle, let's say we say the angle of deflection of mass 1 is theta. The angle that mass 2's final velocity makes with the original direction of motion of mass 1, let's call it phi. And then we can put in that the total momentum has to be the same, put in that the kinetic energy has to be the same, and we basically grind away. Now, there are some problems in the back of the book that relate to this system, and oftentimes you'll be given theta, or you'll be given phi, or you'll be given the initial velocity of the initial guy, and you have to basically just fiddle with these equations until you can sort out the answer. The point is, the momentum equation is a vector equation, so that gives you one equation, one scalar equation for each dimension in space. In other words, the x components of the momenta have to add and equal each other before and after, the y components have to equal each other before and after, and the z components have to equal each other before and after. The most we're going to do in this class is probably two-dimensional collision, in which case you just have two equations from the momentum conservation, the fact that the momentum is unchanged, I should say, and you get one scalar equation from the fact that the translational kinetic energy is unchanged, since this is a perfectly inelastic collision. And basically you just grind away on those three equations, and hopefully you only have three unknowns, and you can solve the thing. So that's the idea. We're going to work some examples in class, and also we'll have a lab this week dealing with collisions, so we can get some experimental evidence that this stuff actually works, and we'll see you there. Hey guys, welcome back. It's time for chapter 11. Now we're talking about angular momentum, and finally we get to our third fundamental principle, and that is the angular momentum principle. So let's do it. I want to begin by describing a situation in which a child runs toward a merry-go-round and hops on the merry-go-round, and the merry-go-round spins. What we discover is that for a given velocity and a given mass, if he runs in such a way that he hops on at the rim of the merry-go-round, it spins fast in the clockwise direction. But if he jumps on a little bit closer to the center, then I should say if the perpendicular distance between his line of motion, his trajectory, and the center of the merry-go-round is smaller, then when he hops on, it turns out the thing spins with a smaller angular velocity. If he runs straight at the center of the merry-go-round and hops on, he can still hop on at the rim, but if his line of motion intersects with the center of the merry-go-round, the thing won't spin at all. And if he actually lands on the thing at a point below the center, shown in the diagram there, then it'll spin, but in the opposite direction and fairly slowly. So he's got the same momentum in all three pictures. The momentum of the boy is his mass times his velocity. The momentum of the merry-go-round is 0. But the resulting motion after he jumps on is very different in these four cases. And the question is, what's actually different here? And the answer is, it's something we're going to call angular momentum. He's got an angular momentum in the first picture that's larger than the second picture. His angular momentum in the third picture is 0. And we'll see that the angular momentum actually sort of has a sign concept. And the sign of the angular momentum, if you want to think of it that way, is opposite in the bottom picture. Now, the way we're going to define angular momentum, it's actually a vector quantity. But it's a little bit different kind of vector than we've dealt with in the past. In order to understand the vector nature, we've got to develop a concept called a cross product. And the cross product of the boy's angular momentum, the cross product of his r vector and his momentum vector, is going to be called the angular momentum vector. The r vector is the vector that goes from the origin of the coordinate system that we're using to compute the angular momentum to the current position of the object, the boy in this case. The momentum vector is the plain old momentum vector we've been using all along. But the cross product is a vector that's actually perpendicular to r and perpendicular to p. And the particular way that we generate that perpendicular vector is the subject of a couple of slides here. But let's suffice it to say for the moment that since v is in the plane of the horizontal plane and r is in the horizontal plane, that you can see that in order to be perpendicular to both of those, the cross product has to be in the vertical direction. So, and it turns out in the first two pictures, the angular momentum points into the page. In the last picture at the bottom, the angular momentum points out of the page. And in the third picture from the top, the angular momentum is actually 0. You can guess, based on the diagram, that probably the angular momentum has something to do with the perpendicular component of the r vector, where the r vector goes from the origin, the center of the merry-go-round, to the boy. So, in fact, it turns out the magnitude of the angular momentum, not the direction, but the magnitude, is the magnitude of the r vector times the magnitude of the p vector times the sine of the angle between the two. And if you look at that a little bit, you'll notice that in fact that means that the angular momentum can be thought of as either the perpendicular component of r times the magnitude of p, or it could be the magnitude of r times the perpendicular component of p. Basically, it's the product of the magnitudes of the two vectors times the sine of theta, which gives you a sense in which the two vectors are perpendicular to one another. If the sine of theta is 1, it means they're exactly perpendicular. If the sine of theta is 0, it means they're parallel, which is the opposite of perpendicular, so they're not perpendicular at all, and so that would correspond to the third picture from the top. The r vector points to the left, the p vector, points to the right. Those guys are anti-parallel, which means they are not at all perpendicular, so you get no angular momentum in that picture. Now let's talk a little bit more about how we actually calculate cross products and what it all means. In some textbooks, they don't worry about cross products. They just talk about clockwise and counterclockwise, and that's okay to a point. The problem with clockwise and counterclockwise is that the clockwiseness and counterclockiseness of a rotation depends on your point of view. If you look at counterclockwise from one side of the chalkboard, if you could go around to the back side of the chalkboard and look at the same rotation, it would appear to be clockwise. And similar with clockwise, it looks like counterclockwise from the other side. So that students sitting on opposite sides of a laboratory bench, for example, watching the same object spin, will report that the object is spinning in opposite directions, but it's the same object. It's not really spinning in opposite directions, it's just that their point of view is different. But the cross product is a vector that lives in three-dimensional space, and it has an unambiguous direction, which is the same for any observer, no matter who's looking at the thing. The cross product of A and B in the diagram you see there points toward the observer in the picture. But if there was another observer on the other side, they would see the same cross product, and it would point away from them, but it would be a fixed direction in space. Similar with the clockwise rotation, C and D. So the advantage of a cross product is that it is unambiguous and absolute. Everybody agrees on what it is. And so once you pick a coordinate system, everybody can consistently label a cross product and get the same answer. Okay, so let's think about how we get the labeling right. The idea is, if you point your fingers of your right hand in the direction of the first vector and face your palm toward the direction of the second vector, if you wrap your fingers from the first vector to the second vector, your thumb will point in the direction of the cross product. So you can see that's true if you go back to the first diagram. If you point your fingers in the A direction and wrap them into the B direction, you get a cross product that points out of the board toward the observer in the picture. On the other hand, if you take the fingers of your right hand and point them in the C direction, wrap them into the D direction, your thumb points in a direction away from the observer in the picture. And it can be quite a contortionist exercise to get your thumb and your fingers pointing in the way they're supposed to, based on the diagram in a particular problem. But the good news is it's worth it, because you get an unambiguous result that doesn't depend on how your textbook is oriented or anything else. The other thing is, if something is spinning, it has what's called a spin angular momentum, which is the sum of the orbital angular momenta of all the pieces of the thing about its center of mass. And we can calculate that quite easily using the concept of rotational inertia, which we've already encountered. But we will need to be able to get an angular momentum vector out of that. And the way we'll do it is to wrap our fingers in the direction of rotation, and our thumb will point in the direction of the corresponding angular momentum. That's the idea. And one other thing I should point out before we move on is that it is often necessary in these problems, since they are inherently three-dimensional. The momentum, the r vector, and the angular momentum point in mutually perpendicular directions, and so we cannot avoid three-dimensional notation and three-dimensional diagrams in many problems. And so we need a convenient way to specify vectors that are perpendicular to the plane of the page. And so the convention that we use is that vectors are actually arrows. They have fletching, they have tips. When the fletching is pointing out of the board, that means the arrow points into the board. So into the page vectors will be denoted by drawing their fletching sticking out, the little feathers sticking out, their X's. If you have vectors pointing out of the board, then the arrowheads are pointing out, and those correspond to little tips. And the dots will be the tips of the arrows pointing out of the board. That's the idea. Okay, let's see how the algebra of this cross-product business works. If I define I hat, j hat, and k hat to be unit vectors that point in the x, y, and z directions respectively, you can see that based on our right-hand rule, knowing that the angle between two unit vectors is 90 degrees and their magnitudes are all 1, that I hat cross j hat is a unit vector perpendicular to each of them, and according to the right-hand rule, you can see that's going to end up being the z direction, or k hat. On the other hand, if you swap the order of j hat and I hat in the cross product, by the right-hand rule, the result is going to point in the opposite direction. So that means that the order of the vectors in a cross product is significant. They're not commutative. You can't just swap the order and get the same answer. In fact, in this case, you can see it turns out to be minus k hat. So then the next thing is you can write out the result of any two unit vectors crossed into each other and see that there are 6 possible combinations. And then you also can see that when you cross them into themselves, you get 0. And so if we take two generic vectors, A and B, and try to compute the cross product, you get a pile of cross terms, but a lot of them are 0, or they reduce to simple unit vectors that point in some other direction. And when the smoke clears, you get the following result. And this result is in the book, and it's on this slide. You should write it down. You can see that you can immediately write down a rule for computing the cross product of any two vectors, given that you have the components of the two vectors. So, and we'll have to do that sometimes. Usually, however, we can look at the picture, use our idea of the right-hand rule, and our understanding that the magnitude of the cross product is the perpendicular component of the first vector times the second times the magnitude of the second, or the perpendicular component of the second vector times the magnitude of the first, or some such thing, in order to compute the cross product. I want to remind you guys of the variables we've been dealing with, like position, velocity, which is the rate of change of position, acceleration, which is the rate of change of velocity, the mass, the momentum, which is the mass times the velocity, the force, for which we have a fundamental principle, the net force is equal to the rate of change of the momentum, and the translational kinetic energy. Now, it turns out in a lot of problems, it's quite easy, or I should say it becomes easy with practice, to identify analogous quantities for rotational motion. So, for example, the analogous quantity of position in rotational motion is the angular position, or the angle. And the rate of change of the angle, of course, is the angular velocity. And the rate of change of the angular velocity is the angular acceleration. Now, there's an analogous quantity to mass. We call it rotational inertia. There's an analogous quantity to momentum, and we call it angular momentum. Now, angular momentum we're learning right now comes in two flavors. There's the kind with the boy running at the merry-go-round. That's orbital angular momentum. That's the angular momentum an object has as a consequence of the fact that its center of mass is moving relative to the origin of the coordinate system. But there's also spin angular momentum, which has to do with the idea that an object is spinning about its own center of mass. And spin angular momentum looks just like translational momentum. Algebraically, it's the rotational inertia times the angular velocity. And then notice that looks a lot like mass times velocity, except it's spin angular momentum. There's going to be something called torque, which we haven't got to yet, but we will, and it's sort of a rotational analog of force. It's a twisting force that wants to make something rotate, and the net torque turns out to be equal to the rate of change of the angular momentum, the total angular momentum, which could include orbital and spin components. But notice the similarity with the momentum principle and the angular momentum principle. The torque plays the role of force, the angular momentum plays the role of momentum. Other than that, they're very similar. And finally, we've already encountered this one, but I just want to point it out, that there is rotational kinetic energy, which is 1/2 times the rotational inertia times the angular velocity squared. This is the kinetic energy of the pieces of a system as it spins with an angular velocity omega. It's the kinetic energy they have as a consequence of their motion moving about the center of mass. The translational kinetic energy is the kinetic energy an object has as a consequence of its motion of its center of mass. So that's the idea. So you can see we end up with alphabet soup. For example, one of the problems we dealt with in Chapter 2 were situations involving a constant net force. If we had a constant net force, we could write down an expression for the displacement. So for example, if we have a constant net force in the x direction, and we know the initial x coordinate, and we know the initial x component of velocity, we can simply write down an exact expression for the position of the object in the x direction, the x coordinate of its position, from the momentum principle. We simply integrate a couple of times, and boom, we've got an answer. The cool thing is, if I know I'm experiencing a net torque that's constant, and an object has a fixed axis of rotation, for example, I can simply replace the net force with the net torque, with the mass with the rotational inertia, the initial velocity with the initial angular velocity, and the initial position with the initial angle. And I get an expression for the final angle as a function of time. I don't have to go back and solve the problem all over again because I already know the form of the solution. I just have to know the relationship between the translational and the rotational concepts. That's the idea. Also, just to point out that the rate of change in momentum is equal to the net force looks a lot like the rate of change of the angular momentum equals the net torque. So the momentum principle and the angular momentum principle are really strongly related by this correspondence between translational quantities and their rotational analogs. Finally, the total kinetic energy of a system is going to be the sum of its translational kinetic energy, its rotational kinetic energy, and its vibrational kinetic energy. And we haven't talked a lot about vibrational kinetic energy, but you can imagine that that has something to do with the radial component of the velocity of the pieces of the system, whereas the rotational kinetic energy has to do with the angular velocity of the pieces in the system. So that's kind of how it works out. Very good. Let's talk about torque. Torque is just a force that tends to make something want to change its angular momentum. So let's say I have a random object acted on by some force, and I want to compute the torque. The answer is I find the angle between the force and the location where the force is applied. Sometimes that's called, there's a concept called moment arm, which is the perpendicular distance between the line of force and the axis of rotation. But it all comes out of this cross product between the r vector and the f vector. The r vector goes from the axis of rotation to the point of application of the force. The f vector is just the force vector, and the torque is the cross product of the two. And as usual, you can either take the perpendicular component of r, which is sometimes called the moment arm, times the force, or you can take the perpendicular component of the force times r. Either way, you get the same answer. Now, what is the rate of change of the angular momentum? It's the rate of change of the torque. I'm saying that wrong. The rate of change of the angular momentum is the rate of change of r cross p by dt. This is in a case where we're talking about orbital angular momentum. Well, using the product rule, that's dr dt cross p plus r cross dp dt. Now I want to point out that dr dt is velocity, and velocity and momentum are always in the same direction. So dr dt cross p is 0. So that means that the rate of change of the angular momentum is really just r cross dp dt, but we already know dp dt is f, so the rate of change of angular momentum is r cross f, and that's the torque. So that's a limited form of a derivation of the angular momentum principle, assuming that the angular momentum is orbital angular momentum. Okay, let's see if we can figure out the spin angular momentum based on our understanding of orbital angular momentum. The spin angular momentum is the orbital angular momentum an object has. I should say it's the sum of the orbital angular momenta all the pieces of an object have relative to their motion about its center of mass. So let's say we have an object that's spinning with some angular velocity, omega. And let's look at a particular piece of it. We know that the velocity of a piece is omega cross r, but let's actually show that. The point is, omega is a vector that points out of the page. That's why omega is a dot. The r vector for a particular piece, it goes from the center of mass to the piece, and so omega cross r has the right direction, because if you point your fingers out of the page and wrap them into the r vector, you get a vector that points in the direction of motion of the object. So the idea is that the direction of the velocity is certainly correct for omega cross r. What about the magnitude? Well, the magnitude is going to be the magnitude of omega times the magnitude of r times the cross product of omega hat and r hat. Well, omega hat and r hat clearly have the correct direction for the cross product, but is omega times r the correct magnitude? And you can see that it is. It's the circumference of a circle of radius r divided by the period of one orbit. So I think everything's okay. The angular momentum, of course, is r cross p. But p is m times v, so you put m times omega cross r, and you end up with this thing m times r cross omega cross r. But if you think about that for a little bit, you'll see that that's mr squared times omega. Omega cross r points in the v direction, r cross v points back in the omega direction, so you end up with mr squared times omega all over again. So a single point has an angular momentum that is mr squared times its angular velocity vector. Notice that we already worked out back in, what, chapter 8 or something, chapter 7, I don't remember now, that the rotational inertia of a point mass is mr squared. So this is just I times omega. That's our old friend. And that's true of each of the point masses in the system. So that means that the total angular momentum is the sum of the mr squareds times omega. And of course that harkens back to our definition of rotational inertia. And so we define rotational inertia to be the sum of the mr squareds. That's kind of the idea. So the angular momentum for the spin angular momentum is the rotational inertia times the angular velocity. The rotational inertia is nothing other than the sum of the mr squareds. Now we already worked this out for kinetic energy, but it works out the same way. If you go to calculate the kinetic energy, it turns out the omegas factor out. The half factors out, and you get this sum of mr squared again. And so the rotational kinetic energy, that associated with the rotation of an object about its center of mass, is 1/2 I omega squared. And I is nothing other than the exact same thing we found before. It's the sum of the mr squareds, or it's the integral of r squared dm. So let's take some examples. If we have a ring where all the mass is at the same radius, or a point mass at a particular r, then the rotational inertia is just going to be mr squared. If we have a rod that's spinning about one end of the rod, say, and we want to know the rotational inertia relative to that axis of rotation, we simply compute dmr squared. Of course, dm is the total mass divided by the total length times dx, and we put that in and we get 1/3 ml squared. We can do the same thing with a uniform disk, which we already worked out in class, but there it is again. Or you could do a sphere, which we haven't worked out, but it's entertaining to do so. You can try it out sometime. So what we like to do is to divide the translational and rotational angular momentum into, or the total angular momentum into pieces, translational and rotational. And the total angular momentum is, of course, the sum of the two. And you can see that that's equal to the total torque acting on the system. So when you plug all that in together, you can see that the rate of change of the translational angular momentum turns out to be the torque on the center of mass due to the net force, and that the rate of change of the rotational angular momentum is the sum of the torques taken about the center of mass. So we'll see how that works in some of the problems. And finally, the last piece is that in a microscopic system, angular momentum is actually quantized. It can only take on certain definite values. So for example, if you think back to the Bohr model we discussed in Chapter 8, the angular momentum turns out to be an integer multiple of h bar. I should say the z component turns out to be an integer multiple of h bar. This is essentially equivalent to the conjecture that the de Broglie wavelength has to fit around an orbit an integer number of times. If you play with this a little bit, you'll see that it turns out to be exactly the same condition. And as we did in class for our group problem solving exercise, you can show that this implies that the orbital radii are quantized, have definite orbital radii, and that orbital radius turns out to be proportional to this n, the same n that quantizes the angular momentum. It gets squared in computing the radius of the nth orbit, and the energies are correspondingly quantized, and if you plug all that in, you'll see that the energies turn out to go like 1/n squared. And these results are familiar to you from Chapter 8, but not until now have we defined what angular momentum is so that we could even talk about where they come from, but that's basically the story. The other thing is that in a modern view of the orbit of electrons, there are no actual circular orbits. Basically what you end up with are probability density clouds of various shapes and sizes. And you can even compute under different circumstances the probability or the rate at which probability transitions from one state to another. But the angular momentum and the energy are quantized in exactly the same way, even in the modern view. The z component of momentum turns out to be an integer multiple of h bar, and the total angular momentum turns out to depend on L times L plus 1, where L is an integer or a half integer. So, for example, if you're talking about orbital angular momentum, L would be an integer, but the spin angular momentum of a particle turns out to be half integer for most matter particles like protons and electrons and things like that, neutrons. So it gets quite interesting, but I just wanted to point out that this angular momentum concept works all the way down to the microscopic scale, with the minor change that it turns out it gets quantized at that point. So that's the end. We'll see you guys next time. Hey guys, welcome back. It's time for Chapter 12 on entropy. So the first thing I want to do is a little demo to describe for you how we're going to treat a solid in terms of the thermal energy associated with the vibrational motion of the atoms in the solid. So let's take a look at that. So here we have a simulation of a crystal, and it's basically a chunk of matter that is made up of atoms connected side to side, and you can see that everybody's sort of wiggling around. And the question is, how can we treat this as a collection of oscillators? And one way would be just to focus on one atom at a time. Let's think about how that might work. Okay, so here we have a three-dimensional model of an atom stuck inside a cube where the spring is connected to the walls of the box. Now this is obviously not quite right because it's really embedded in a crystal that goes on in all directions with neighboring atoms next door and so on. But for the purposes of our work today, we're going to use this as a simple model of what's going on. Now the interesting thing is, because it's a quantum mechanical object, we know that we have to somehow work out the energy levels that are permitted for this thing to have. Now the interesting thing is, because the potential energy goes like 1/2 kx squared plus 1/2 ky squared plus 1/2 kz squared, you can actually separate this out into x, y, and z directions and solve the quantum mechanical problem with each direction more or less acting independently. Now, the details of how that works are sort of beyond the scope of what we're doing here. The bottom line is that a three-dimensional atom stuck in a crystal behaves a lot like three independent one-dimensional masses connected to a spring. And we know that right now these guys are all three in their ground state, but we can excite the thing in the x direction, and now you see it's wiggling with a little bit more energy in the x direction. I could make it wiggle more, and yet more, and yet more, and now you see it's in the 1, 2, 3, the fourth excited state in the x direction, but in the y and the z direction it's still in the ground state. Now because the spacing of the energy levels is the same in all three directions, because presumably the spring constant is the same for all three directions, I could keep the total energy the same by dropping the x direction down 1 and bumping the y direction up 1. Or I could drop the x direction down 2 and bop the y direction up 2. Or I could bop the y direction down 1 and bop the z direction. So in other words, any superposition or any combination of 1, 2, 3, 4. So here I have 1 in the z, 1 in the y, and 2 in the x. That's the same total energy as I had before, with 4 in the x and 0 in the y and the z. Anyway, you kind of get a sense of physically what's going on inside the crystal for different amounts of energy in the different directions of motion. Alright, so that's the idea. Okay, so let's see if we have an atom in a box. This of course represents one atom out of our crystal, and we let it wiggle around. What we want to figure out is how many ways are there to distribute the energy. In this case, the example I want to do is 4 quanta of energy among the 3 oscillators associated with the 3 different directions of motion. So you could of course put all 4 quanta into one direction. So you could have 4 in the x and none in the y and none in the z. Or you could have 4 in the y and none in the x and none in the z. Or you could have 0 in the x and 0 in the y and 4 in the z. So there's 3 ways, but that's not the only way. You could also distribute 2 in the x, 2 in the y, and 0 in the z, and so on. So there's 6 different ways to store 2 in one and 2 in the other, or 2 in one and 1 in the other and 1 in the other, and stuff like that. And finally there's another 6 ways, and that is if we put 3 in the first one and 1 in the second and none in the third, and so on. So altogether, let's see, we've got 6 and 6, that's 12, and then 3 more makes 15. So if you look at all those, there are 15 possible ways to distribute 4 quanta among 3 oscillators. So the variables we're going to be using in this class to describe those 3 quantities are omega, which is the number of ways, q, which is the number of quanta, and n, which is the number of oscillators. So each of these ways, these 15 ways, is called a microstate. In other words, it's a microscopical distribution that's different from the other microscopical distribution, but they all have the same property, that their total amount of energy is 4 quanta. So the fact that there are 4 quanta is called a macrostate, because if you just care about the total energy, then you don't care about exactly how it's distributed, and so those all belong to the same macroscopic behavior. In statistical thermodynamics, we're going to assume that every microstate is equally probable. So that means that no microstate is any better or worse than any other microstate. And if you wait around long enough, they'll all be visited with equal likelihood. That's kind of the idea. In the end, when we're calculating the flow of energy from place to place, it turns out we don't really need to know the details of all the distributions. We just need to know how many ways there are to distribute the energy with a particular total value. So let's march ahead and see what happens if we have two atoms that are sort of connected together somehow, so they can exchange energy, but the total energy in the two atoms is going to remain fixed. So let's look at how that might work. How many ways can one atom have 4 and the other atom have none? Well, there's only one way an atom can have no energy, and that's if all 3 are 0. And so 15 has to be the answer to that question. How many ways can one have 1 and the other have 3? Well, you can have one unit in 3 different ways, either 1 in the x and 0 everywhere else, or 1 in the y and 0 everywhere else, or 1 in the z and 0 everywhere else. And it turns out there's 10 different ways to distribute 3 quanta among 3 oscillators, which you can show yourself if you want to play with it. And so that means altogether there are 30 different ways of one having 1 and the other having 3, because you have to multiply the number of ways the first one can have 1 by the number of ways the second one can have 3 in order to calculate the total number of ways that they can have 1 and 3. And if you keep going like that, you'll end up with a result that looks something like this. That the number of ways the first atom can have no quanta and the second atom can have 4 is 15. And then it's 30 for the first one to have 1 and the second one to have 3. And it turns out to be 36, I think, for the first one to have 2 and the second one to have 2. And of course, if the first one has 3 and the second one has 1, that's no different from the first one having 1 and the second one having 3, and so on. So it's a symmetrical distribution in this case, since each atom has the same number of oscillators. And it turns out the most likely situation is that they each have 2, because that has the greatest number of microstates associated with the macrostate. So the next question is, if I gave you 50 oscillators and asked you how many ways there are to put 12 quanta on 50 oscillators, for example, that would be a very difficult calculation to work out by hand like this. So what we'd like is a formula that enables us to get the answer without having to work it out by hand, by counting one by one. So this is really a game of combinatorics. So the idea goes something like this. We're going to come up with a trick to help us count the number of ways of having 4 quanta in 3 oscillators using a sort of a graphical representation that will enable us to then generalize. So let's look at the picture. The 310, 301, 130 set. I want you to imagine a situation where you have partitions that tell you when you move from one atom to the next, and dots that represent the amount of energy. So for example, the first on the left there, in the upper left, is 3 quanta in the first oscillator, 1 quanta in the second oscillator, and 0 quanta in the third oscillator. So we could represent that with 3 dots, and then a partition, and then 1 dot for the 1 quanta in the middle, and then a partition, and then no dots. Notice that with 3 oscillators, we have 2 partitions to separate the boundary between the one on the left and the middle, and the one in the middle and the right. So there's 3 minus 1 partitions, and because there's 4 quanta, we have 4 dots. And quickly, you can see how this goes for the other situations. We got 3, 0, 1. We've got 1, 3, 0. We've got 0, 3, 1, 1, 0, 3, and 0, 1, 3. So those are all the combinations that correspond to 1, 3, and 0. And just as an example, we could also do 4, 0, 0, 040, and 004. And you can see you could also do 211 and 220 and so on. The interesting thing is this. If you think of 4 dots and 2 partitions as generic objects, what we really want is all possible combinations of these 6 things, but we don't care about the order of the dots or the order of the partitions, or for that matter, even the relative order of the 2. We just want to know how many ways are there to take 6 things and put 4 of them in different places. So that's a standard problem in combinatorics, and here's the way you think about it. If I had 6 distinct things like A, B, C, D, E, F, there are 6 factorial ways to order A, B, C, D, E, F, because I could put the first thing down in 6 places, and then if I've got 6 empty spots and I can lay the letters A, B, C, D, E, F down in any order, there's 6 ways to do the first letter, there's 5 ways to do the second letter, 4 ways to do the third letter, and so on. And so altogether, if I care about the order of the letters, I would have 6 factorial ways of doing it. But if I group them in a group of 4 and a group of 2, and I don't care about the order of the group of 4 or the group of 2, then I have to divide by the number of ways to lay out 4 things, and then also divide by the number of ways to lay out 2 things. So I'd have to divide by 2 factorial times 4 factorial. So this expression, 6 factorial divided by 4 factorial times 2 factorial, is a standard number in combinatorics. It happens to be called the binomial coefficient, because it also shows up when you take a binomial to a power, you end up with the same number, basically, and it also shows up in Pascal's triangle. So I can show you in class, if you're interested, how this relates to Pascal's triangle. But the short story is, it also tells us how many ways to order 4 quanta in 3 oscillators. Notice that if I have 6 factorial upstairs and 4 factorial downstairs, that 4 times 3 times 2 times 1 all cancels because it's in the numerator and the denominator. And 6 divided by 2, of course, is 3, so the answer turns out to be 3 times 5. So omega is 15. Now that's the answer we got before, but you can see now how you could get the answer in general. If I have, let's say, 12 quanta in 7 oscillators, I could take 12 plus 7 minus 1, that would be the number of spaces, factorial, divided by 12 factorial times 7 minus 1 factorial. So I could compute, in principle, for any number of quanta with any number of oscillators, I can calculate the number of ways in general. So the formula that we're going to be using is this one, q plus n minus 1 factorial over q factorial times n minus 1 factorial, where n is the number of oscillators and q is the number of quanta. Okay, so let's look at another demo to see how that turns out. Okay, so here's a simple program. You guys will be working with this in the lab, but the idea is you've got 50 oscillators, and you put 30 of them in one object and the remainder in another object, N1 and N2. Take a total of 30 quanta and then compute the number of ways of having that many quanta in object 1 and object 2. So you start with quanta in object 1 at 0. The quanta in object 2, of course, would be 30. And then you calculate the number of combinations for object 1, the number of combinations for object 2. The product will give you the total combinations for both objects, and then you plot that as a histogram. If we run this program, you'll see what we get is something sensible. So it looks like there's a peak in the total number of combinations at around 18, which, if you think about it, that's about 60% of 30. So 60% of 30 corresponds to 60% of the energy in the object with 30 oscillators, and 40% of the energy in the object with 20 oscillators. So anyway, that's the idea of that one. Okay, now let's talk about entropy. So entropy is defined in terms of the number of microstates that are available in a certain macrostate. The thing is, in order to be consistent with the historical definition of entropy, it turns out we need to take the natural log of the number of microstates. As you saw, the number of microstates grows very quickly because it's got factorials in it. Factorials grow very quickly, and taking the log has a couple of advantages. One is it makes the numbers much more reasonable to deal with, and the other thing is it works more naturally if you've got multiple systems that get combined into a bigger system. The entropy turns out to be easier to think about for reasons that we'll get to here in a minute. So the definition we're going to use for entropy is the Boltzmann constant, K. Sometimes that's K sub B. If there's a K in the problem, like a spring constant, it's useful to use K sub B as the Boltzmann constant, and then K can be the spring constant. And it's times the natural log of the number of microstates. So the Boltzmann constant is 1.38 times 10 to the negative 23rd joules per Kelvin. Okay, so here's a similar one, except that this time we're graphing the logarithm of the number of ways, and that's going to be proportional to the entropy. So entropy is the logarithm of the number of ways, the same combination calculation we're doing this time. And remember that the logarithm of the product is the sum of the logarithms. So as you can tell when you see the graph, there it is. This is the number of ways for Q1 to be distributed among N1, and as Q1 gets big, the number of ways go up and the logarithm goes up. Here the logarithm drops as the number of ways of putting Q2 in object 2 goes down. The sum of Q1 and Q2, remember, is 100. And it turns out the product of the two has a logarithm that's equal to the sum of the logarithms of the individual number of ways. And so this is what we call the entropy. And notice the entropy has a maximum right around in here, which is also about 60, what is it? Around 67% or 60%, I guess 60%. Yeah, 60% of the total. When 60% of the oscillators are in the object that has 60% of the 60% of the quanta are in the object that has 60% of the oscillators, and 40% of the quanta are in the object that has 40% of the oscillators. That's the condition for a maximum number of ways, or maximum entropy. So that's the idea. So let's look at this. If I have so on the left I have a picture that shows two blocks of matter, one of which contains 300 oscillators, the other of which contains 200 oscillators. And let's assume that between the two of them they have a total number of quanta of 100. So we have 100 quanta distributed between two blocks of material, one of which has 300 oscillators and one of which has 200 oscillators. And the question is, what is the most likely distribution of energy? And the answer is that it's the distribution where the number of ways of having the energy distributed in that way is a maximum. So notice that as you increase the number of quanta in block 1, the number of ways that you can put that many quanta in block 1 goes up, but you do that at the expense of the number of quanta in block 2. If the number of quanta in block 2 goes up, its number of ways also goes up. What is the most likely? The most likely is the situation where the number of ways is maximized. We're going to find out that that's also the same thing as maximum entropy. So if you start the thing out with 90 oscillators in the orange block and 10 oscillators in the blue block, and you wait around a while, it naturally reaches equilibrium. It reaches the state where they have the maximum number of ways, and that turns out to be when the 300 oscillator block has 60, that would be block 1, and the 200 oscillator block, block 2, has only 40. That's kind of the idea. So, and what is the condition for equilibrium? Well, you could say it's the point where the maximum entropy occurs, the maximum number of ways occurs, and that's correct. But if you look at the graphs for entropy versus Q for the two blocks, notice that if you're to the right of equilibrium, the slope of the sort of purplish line, the line for Q2, is greater in magnitude than the slope of the orangish line, the slope for block 1. If you look at the graph on the right here, for example, the blue slope is greater than the orange slope in magnitude, which means if you move to the left, the entropy goes up more for block 2 than it goes down for block 1. So that would produce a net increase in entropy. If you continue going to the left, you reach a point where the slope of the orange is greater than the slope of the blue, and in that case you'd be going down more than you're going up. You'd be losing more entropy in the orange than you'd be gaining in the blue, and so the total entropy would fall. And the condition for having a maximum in the entropy is when the slopes of those two lines are equal. If the slope of the blue is the negative of the slope of the orange, it turns out the slope of the sum is the sum of the slopes. That points out another nice thing about taking the natural log. If you've got the number of ways of having two systems have a certain partition of energy, is the number of ways for system 1 times the number of ways for system 2. But when you take the natural log, the entropy of the total system is the sum of the entropy of the first and the second. And that's because the log of a product is the sum of the logs. And so the sum of these two entropies is what matters, and it turns out that the condition for equilibrium is that the slope of the entropy versus Q graph is the same. But of course Q is another word for energy, because the number of quanta in a particular block is proportional to the energy in the particular block. So you end up with the definition of temperature that's 1 over the slope. If you think about that, it means that the greater the slope, the lower the temperature. The lower the slope, the higher the temperature. And that also makes sense with regard to these graphs, because notice that as Q goes up, the slope becomes diminished. So the lower the slope, the more energy in the system, and the higher the temperature. So that's the idea. Let's also talk about specific heat capacity. If we have a block of material and we heat it up, its temperature is going to rise. The specific heat capacity, of course, is the heat capacity per atom. In this case, we're talking about the atomic specific heat capacity, not the mass specific heat capacity. So it's the change in the energy per atom per degree Kelvin. And that means as we increase the energy in the system, we're also going to increase the temperature. So and the way this works is you find the energy at one value of Q in the system, then you go to the neighboring values of Q, and you compute the change in the entropy per Q, and then you calculate the change in the energy per Q, get the temperature, and then calculate the heat capacity using the definition of heat capacity. So I've got a couple of spreadsheets that I think will help you see how that works. Hey guys, so I've got a little problem here. Particle A is 4 atoms with 1 quantum of energy. Particle B is 2 atoms with 2 quanta of energy. And the notion is that they share the energy back and forth, and we want to figure out where equilibrium lies. Now, because particle A has 4 atoms, notice that each atom has 3 degrees of freedom, so that's 12 oscillators. Particle B has 2 atoms, that's 3 degrees of freedom per atom, so that's 6 oscillators. Okay? And we know that particle A starts with 1 and particle B starts with 2, so that means we have a total of 3 quanta of energy. So I'm going to start Q, the total number of quanta in the system, at 3. So we're going to begin our table with particle A with 0 quanta, and particle B is going to have 3 minus 0. But I wrote 3 minus 0 in kind of a strange way. Let's look at it. It's B1 minus A6. That means take whatever's in this cell and subtract whatever's in this cell. Now, normally, if you just say B1, and we're currently in B6, that means 1, 2, 3, 4, 5. That's the cell 5 rows up from the current cell. And A6, similarly, is the cell 1 row to the left of the current cell. Now I want to keep the 1 row to the left thing, because when I drag this formula down, I want to get the number of quanta in particle A each time. But the 3, I don't want to move where that's coming from, so I'm going to come up here to this and tell it it's absolute. I put dollars in front of the B and dollars in front of the 1. That makes it an absolute reference. Okay. Now, what about this row? I want this to be 1, but I'm going to write it in a funny way. I'm going to write it as equals whatever's in the cell above me plus 1. Notice that the cell above me has a 1 in it, or a 0 in it, so 0 plus 1 is 1. But now if I drag this down, it automatically fills in with the cell above plus 1, the cell above plus 1. So I get 0 through 3. And notice if I drag this formula down now, because of the way it's written, I get 3, 2, 1, 0. So this is the number of quanta in particle B given that A has 0. This is the number of quanta in particle B given A has 1, and so on. Notice the sum always adds up to 3, as you'd expect. Now, let's do the following thing. I want to calculate the natural log of the number of combinations for particle A, but let's do it in 2 steps. First, I'll use the combinatorial function to calculate the number of combinations of ways of getting 0 quanta in 12 oscillators. But notice how we do that. We take the number of quanta plus the number of oscillators. Sorry, let's write it this way. Plus the number of oscillators minus 1. That's the total number in my set of objects, and I want to take them out q sub a at a time. So that's A6. So my formula is going to be, let's go look at it, A6 plus B2, so that's Q plus N minus 1, take Q. Now the problem is, of course, B2 here, the number in particle A, that needs to be absolute because I always want it to go back and get the 12. So I'll put that in with dollar signs, and you can see that we get the number of combinations of 3 oscillators, or 3 quanta in 12 oscillators, 364. That's a lot easier than calculating it by hand. But actually what I want here isn't that. So this is the number of combinations, but what I really want is the natural log of the number of combinations. So I'm going to come back up here and make this ln combinations. And then that's going to turn the 1 into a 0, and it's going to turn these other numbers into the log of the corresponding number of combinations. So that's how that works. Now I could copy this over to here, and I'd get B6. Actually, that's what I want for particle B, except I don't want $B $2. I want $B $3. So let me edit this. Actually, I can just bring it down like that. $B $3. And now I've got the natural log of the number of combinations for particle 3. And notice it goes from 4 to 0. This goes from 0 to almost 6. And how do I get the natural log of the product of omega A and omega B? Well, it's obviously just the sum of the natural log. So here I'm just going to put this plus this, and then I'll drag that down. Whoopsie. Seem to be getting, there we go. So now you can see this is the log of the product, and this is proportional to the entropy. So you can see that the maximum happens at when QA is 2 and QB is 1. In other words, the situation in which the number of quanta is in the same proportion as the number of oscillators, 2 to 1. So that's not totally surprising, and that's kind of the way it works. Okay guys, here's a similar example. We got a one-dimensional row of objects. There's 5 of them. Each has a certain mass. Each has a certain spring stiffness, and we're going to compute the entropy as the number of quanta goes from 0 up. So like we did before, we'll start the number of quanta at 0. We'll add 1 each time, like so, and I'll bump those up, up. And then we'll calculate the number of ways of putting Q quanta into N oscillators. That's going to be combine of Q plus N minus 1, and then comma Q again. And remember that the N needs to be absolute, so we'll put that in, and we'll calculate that. Alright, now we need the entropy. So the entropy is the Boltzmann constant, which I've already stuck in here, times the natural log of the number of microstates. So we're going to set that equal to the Boltzmann constant, which of course needs to be absolute, multiplied by the natural log of the number of microstates. And that gives us the entropy. Obviously, when there's only one way to do it, there's no entropy, 5 ways, and so on. Now what about the energy? So up here I've put the change in energy
is h bar times the square root of k over m. K is 15 newtons per meter times 4. So the point is, in the Einstein model, we break each spring in half and hold it still. Imagine putting each atom in a box where the walls of the box are fixed, and so that means we break the spring in half. That doubles its spring constant, and also there's one on this side and one on that side, so that gives us 4 times the spring constant. So we get 4 times the spring constant divided by the mass, and that gives us a energy per quantum of excitation. Okay, so the energy in the qth state is going to be simply Q times dE, but of course dE needs to be absolute because it's in a table up there at the top. So we can go down, and now we have the energy for every state. So we've got the entropy and we've got the energy. Let's go down and see what the next question is. We want to know the temperature of the system when the total energy is 4 quanta. So to get the temperature, we need to take the change in energy divided by the change in entropy. So the idea here is we take the energy of the next higher Q minus the energy of the next lower Q divided by the entropy of the next higher Q divided by the entropy of the next lower Q. And that gives us a temperature. So when we have 1 quanta of energy, the temperature is 207.16 Kelvin. We'll go ahead and, it's easy with the spreadsheet, we can just go all the way up. We can't do the last one because it doesn't have a next higher energy, but we can get all the way up to Q equals 6. And the question is, what's the temperature when Q equals 4? So the answer is it's 460 Kelvin. Now, how do we get the heat capacity? Well, to get the heat capacity, we need to take the change in energy divided by the change in temperature. So we'll do that here. I only have temperatures defined starting at Q equals 1, so I can only get the heat capacity starting at Q equals 2. So it's temperature at 3 minus temperature at 1 divided by temperature at energy at 3 minus energy. Oh, I'm doing this backwards. Daggone it. Okay, so it's the change in the energy divided by the change in the temperature. So it's the energy at 3 minus the energy at 1 divided by the temperature at 3 minus the temperature at 1. And that's the heat capacity for all 5 objects at Q equals 2. Of course, I can bump this up. There we go, bump this up and go all the way up to here. I have to stay within the bounds of my temperature. So it looks like at Q equals 4, the heat capacity of the entire chain is 5.3 or so times 10 to the negative 23rd joules per Kelvin. But the problem asks for the heat capacity per object. So it wants to know the heat capacity per object at 4 quanta. 4 quanta is here. So the heat capacity per object is this number, the heat capacity of the whole chain, divided by the number of objects in the chain, which in this case is 5. So we want to take the heat capacity of the whole chain divided by 5. And we can calculate that. And you can see it's a little bit less, about 75 or 78% of the Boltzmann constant. So the heat capacity per object is getting close to, but it's not quite equal to, the Boltzmann constant. So that's how you get heat capacity, is using this kind of calculation. Okay, finally I want to show you a slide. This is an example that shows you the heat capacity as a function of temperature for an elemental solid. At low temperatures, the heat capacity goes to 0. And at high temperatures, the heat capacity reaches an asymptotic value of around 3 times the Boltzmann constant. That's the heat capacity per atom in the material. And that turns out to be a universal behavior of practically all elemental solids. So what that means is we know that all elemental solids basically have the same high temperature heat capacity, and high temperature depends upon the frequency of natural frequency of vibration of the atoms in the solid. And for most practical purposes, most elemental solids at room temperature are in the asymptotic domain. So that means we can just assume 3 kb per atom and calculate the heat capacity of a solid directly.
So that's the main result of that thing. Oh, let's talk about the Boltzmann distribution. What the idea here is that we've got a large reservoir connected to a small system. And the question is, what's the probability of having different amounts of energy in the small system? The key is to find the number of ways to have an energy total of E total, while the small system has an energy of E. It turns out the more energy you give the small system, the greater its entropy is going to be, but at the cost of taking entropy away from the big system. And the most likely case is where the entropy, of course, is maximized. So let's take a look at that. The probability of having any particular amount of energy is the product of the number of microstates in the reservoir times the number of microstates in the small system divided by the total number of microstates regardless of E. So let's take a look at that. So we start out by taking the log of the expression from the last page, and then notice that the K times the natural log of omega of the reservoir is just the entropy of the reservoir. We need to add to that the entropy of the little system, and to calculate the probability, we're going to, since we divided by the log of omega total, we're going to subtract K times the log of omega total here. Now, focusing on the entropy of the reservoir, if you look at the diagram there to the left, notice that the reservoir is very, very large, which means that if we take a little bit of energy out of the reservoir, it's not going to change its temperature very much. And the impact of that is that the slope of the entropy versus energy for the reservoir is almost constant for all reasonable values of E, the energy in the small system. So we can calculate the entropy of the reservoir at some particular value of E by subtracting the slope of the entropy versus the energy times the amount of energy we take out, and add that to the entropy the reservoir would have if it had all the energy. That's the idea. So, but wait a minute. ds dE is minus 1 over t. So what that means, I'm sorry, ds dE is 1 over t. So what that means is we can replace the derivative of the entropy with respect to the energy with 1 over the temperature, and put that back in to the expression for the probability, and then solve for the probability, and we get a nice expression that says it's the number of microstates of the small system that have a certain energy. That's sometimes called the degeneracy, and it's multiplied by this exponential factor, which is called the Boltzmann factor, which tells us that the probability of having more energy is less than the probability of having less energy. And we encountered this factor for the first time way back, I think, in chapter 6, or maybe it was chapter 8. But anyway, we encountered this probability a long time ago, and only now, when we got to entropy, could we figure out where it came from. Don't worry too much about this derivation. It's a little bit subtle, it's a little bit sneaky, but the result is very important, and you certainly should remember the result. So that's the idea. Now there are some examples, like for example, the pressure in the atmosphere goes down with altitude, and that's a consequence basically of this factor. The rotational, vibrational, and translational energies that atoms and molecules can have, different energies have different probabilities, and part of that is this exponential factor. At a given temperature, the probability of having a certain energy is given by this Boltzmann factor. And that also works out the speeds of molecules in a gas. It comes out to be the same exact factor, and so on. So there'll be some homework problems that permit you to sort of exercise how this works, but that's the main idea. So that's all for this time. I hope you guys have a good week with me gone in Denver, and I look forward to seeing you again on Monday.